Hello there, and welcome to Science for Sleep, the quiet corner of the universe where curiosity slows down, science takes a gentle stroll, and complex ideas are explored at a pace comfortable enough to drift off to. Tonight, we're going to wander into a rather intriguing cosmic possibility. Not something loud or catastrophic right away, but something subtle at first, distant, almost unnoticed. Imagine a planet that does not belong to any star. A world drifting through the vast darkness between solar systems. No sunrise, no sunset, just endless interstellar night and the quiet pull of gravity guiding it along an invisible path through the galaxy. These wandering worlds actually exist. Astronomers call them rogue planets, and there may be billions of them travelling through the Milky Way. Some were once part of planetary systems like ours, but were flung outward by gravitational chaos long ago. Others may have formed alone, never bound to a star at all. Most of them wander silently through empty space, passing between the stars like travellers crossing an enormous desert. But tonight's question is a little more personal. What if one of those lonely worlds drifted into our solar system? Not tomorrow. Not in some dramatic movie scenario where alarms blare and governments panic. Instead, imagine something slower. Something that begins far away, beyond the familiar planets, where sunlight is already faint and cold. Out there, movement can take years or centuries before anyone notices. Before we get too deep into that possibility, though, I'd like to ask you something simple. Where in the world are you listening from tonight? Maybe you're curled up under a blanket. Maybe you're sitting quietly with headphones. Perhaps it's late evening where you are. Or maybe the sun has already set and the world outside has gone quiet. And another small question that feels oddly fitting for tonight's topic. What time is it where you are right now? It's funny how something as universal as time can feel so personal. Across the planet, people are listening from different time zones, different cities, different continents, all arriving at this same moment from their own place in the day. Some of you might be just beginning your night. Others might already be drifting towards sleep. If you find this kind of quiet exploration relaxing or interesting, feel free to give the video a like and maybe subscribe to the channel as well. It helps this calm little corner of science reach more curious minds who might enjoy a peaceful journey through the universe before sleep. Now then, let's return to our wandering planet. To understand what might happen if such an object entered our solar system, we first need to step back and consider just how enormous space really is. When people imagine the solar system, they often picture a neat arrangement, the sun in the middle, planets spaced evenly around it like ornaments on a mobile. Mercury close in, then Venus, Earth, Mars, the asteroid belt, and the giant planets farther out. In illustrations, everything looks tidy. In reality, the distances involved are staggering. If the sun were the size of a basketball sitting in the centre of a large field, Earth would be a tiny grain of sand roughly 26 metres away. Jupiter would sit more than 130 metres from the sun, still within the same field but quite distant. Neptune, the outermost major planet, would lie almost half a kilometre away. And beyond Neptune, the solar system continues, farther still. Past the Kuiper Belt, where icy dwarf planets drift slowly through dim sunlight, and outward toward the vast spherical halo of the Oort cloud, a region filled with ancient cometary debris left over from the early days of planet formation. That cloud may extend halfway to the nearest star, which means that between stars there is a tremendous amount of empty space where wandering planets could pass without ever coming close to another solar system. The galaxy is wide enough to hide countless travellers. Astronomers didn't always know rogue planets existed. For a long time, planets were assumed to form only around stars, held in stable orbits by gravity. That idea seemed logical. After all, every planet we knew about in our own system circled the Sun, but over the last few decades, observations began to suggest something unexpected. Some planets don't stay where they formed. Planetary systems are surprisingly chaotic places during their early stages. Newly formed planets tug on each other with gravity, shifting orbits, scattering smaller bodies, and sometimes flinging entire worlds outward like cosmic billiard balls. If a planet passes too close to a larger neighbour during these early gravitational interactions, it can gain enough speed to escape its star entirely. One close encounter with a giant planet can send a smaller world sailing into the darkness between stars. Once that happens, the planet becomes a wanderer. It carries whatever atmosphere it might have, whatever moons might still orbit it, and whatever internal heat still lingers deep beneath its surface. Then it drifts, for millions or even billions of years, cold, silent, and almost invisible against the background of space, yet invisible does not mean non-existent. Astronomers have detected rogue planets through clever techniques that rely on gravity itself. One method is called gravitational microlensing. When a massive object passes between Earth and a distant star, its gravity bends the light from that star, briefly making it appear brighter. If the object doing the bending is a rogue planet, the brightening event lasts only a short time. From those tiny flashes of light, scientists can estimate the presence of objects drifting through the galaxy. The results have been surprising. Some studies suggest there could be as many rogue planets as stars in the Milky Way. Perhaps even more. If that's true, the galaxy may be filled with these quiet travellers, each following its own slow path through interstellar space. Most of them will never come anywhere near us. Space is simply too vast. But occasionally gravity nudges objects onto trajectories that cross paths with star systems, including ours. Now, if a rogue planet were heading toward the solar system, it would approach from the deep outer regions where sunlight barely reaches. Out there, even our most distant probes would see only faint glimmers of reflected light. The first hints might not come from telescopes pointed at the planet itself. Instead, the earliest clues might appear in the motions of smaller objects. Far beyond Neptune lies a region filled with icy bodies that orbit the Sun in wide, slow paths. These distant objects act a bit like cosmic test particles, quietly tracing the gravitational landscape of the solar system. If something massive approached from outside, their orbits would begin to shift ever so slightly. At first, the changes might be subtle. A comet that appears slightly earlier than predicted. A distant dwarf planet whose orbit drifts a fraction of a degree from where it should be. Nothing dramatic. Just tiny irregularities in the motion of distant objects. Astronomers are quite good at noticing such things. Planetary motions are calculated with extraordinary precision, and even small deviations can raise questions. In fact, that's how Neptune itself was discovered in the 1800s. Scientists noticed that Uranus was not moving exactly as predicted, and the best explanation turned out to be the gravitational pull of another unseen planet farther out. Mathematics led the way. Telescopes followed. If a rogue planet were approaching from the outer darkness, the process might unfold in a somewhat similar fashion. At first, a few researchers might notice that certain distant objects are behaving strangely. Orbital calculations would be rechecked. Data would be compared. Perhaps at first the anomalies would seem small enough to ignore. Astronomy is full of tiny measurement errors and subtle gravitational interactions that can complicate predictions. But if the deviations continued, if they became consistent, curiosity would begin to grow. More telescopes would be pointed outward. Observatories across the world would compare observations. Somewhere in that distant region beyond the familiar planets, something would be tugging gently on the solar system, and gradually, slowly, a faint object might begin to reveal itself. Not bright like a star, not glowing like a comet, just a dim, moving point of reflected sunlight creeping through the darkness. From that moment onward, scientists would begin calculating its path. Where is it coming from? How massive is it? How close will it pass to the Sun? And most importantly, what effect will it have on everything else here? Because gravity does not operate politely. It does not ask permission before reshaping the delicate balance of orbits that has existed in the solar system for billions of years. Every planet, asteroid and comet is part of a complex gravitational dance, and introducing a new dancer, especially a large one, can change the rhythm. Yet at first, life on Earth would feel completely normal. Days would pass, the sun would rise and set. No one looking up at the night sky would notice anything unusual. The approaching world would still be too far away to see with the naked eye. But in observatories and research centres around the world, calculations would continue. Simulations would run. Scientists would begin exploring possibilities. Some trajectories might show the rogue planet passing safely through the outer solar system before drifting away again. Other scenarios might reveal something more complicated, because if the wandering world passed near the giant planets, Jupiter, Saturn, Uranus, or Neptune, their enormous gravitational fields could interact in unpredictable ways. Planetary orbits that have remained stable for billions of years might shift slightly, not instantly, not catastrophically, just enough to begin changing the long-term dynamics of the solar system. And those small gravitational whispers would continue travelling inward, toward the familiar worlds closer to the Sun. But before anything dramatic could happen near Earth, the outermost regions of the solar system would feel the disturbance first. Far beyond the warm light of the Sun, where icy bodies drift slowly through deep space, gravity would begin quietly rewriting the paths of ancient objects that have circled the Sun since the beginning of the solar system. Far beyond the warm light of any star, there are worlds that travel through the galaxy completely alone, not in orbit around a sun, not circling a distant star, not tied to any planetary family the way Earth belongs to ours. Instead, they drift, slowly, quietly, crossing the enormous dark spaces between stars like silent travellers moving across an endless cosmic ocean. Astronomers call these objects rogue planets, and for a long time the idea that such worlds could exist seemed almost strange. Planets, after all, were supposed to belong somewhere. The very definition of a planet once implied that it orbited a star, held in place by gravity like beads on an invisible string. Yet the universe rarely obeys our expectations so neatly. Over the past few decades, astronomers have gathered more and more evidence that planets do not always stay where they are formed. Some are cast out of their original homes, flung into interstellar space by gravitational encounters long ago. Others may have formed alone, collapsing from clouds of gas without ever finding a star to orbit. The result is a population of wandering worlds scattered across the Milky Way, and there may be far more of them than anyone first imagined. To appreciate just how remarkable this is, it helps to remember how our own solar system came into existence. Roughly 4.6 billion years ago, a giant cloud of gas and dust collapsed under its own gravity. The densest region at the centre eventually ignited nuclear fusion, forming the Sun. Around it, a spinning disk of material slowly began clumping together. Tiny grains of dust collided and stuck. Pebbles became rocks. Rocks gathered into planet-sized bodies. Over millions of years, gravity shaped those scattered building blocks into the planets we know today. But the early solar system was not a calm place. Young planetary systems are messy environments. Newly forming planets tug on each other with enormous gravitational forces, pulling their orbits this way and that. Some worlds migrate closer to their stars, others drift outward, and occasionally a close encounter sends one body hurtling away at incredible speed. Picture a crowded ice rink where skaters occasionally bump into each other. Most glide past one another without incident, but sometimes a collision sends someone sliding across the ice much farther than intended. In a similar way, planets can be scattered. One strong gravitational encounter with a giant planet can be enough to accelerate a smaller world beyond the escape velocity of its star. Once that happens, the planet is no longer bound to that system. It simply continues travelling forward. no longer a planet in the traditional sense, but still very much a world, a rogue planet. For a long time, astronomers suspected these objects must exist, but detecting them was extremely difficult. After all, planets do not shine with their own light. They reflect light from stars. Remove the star, and the planet becomes almost invisible against the darkness of space. Finding such an object is a bit like trying to locate a black marble drifting through a vast, dimly lit room. Yet scientists eventually found clever ways to detect them. One of the most successful methods involves a subtle effect predicted by Einstein's theory of general relativity, gravitational microlensing. Gravity, as it turns out, bends light. When a massive object passes between Earth and a distant star, its gravity warps the space around it, causing the star's light to briefly brighten and distort. If the object doing the bending is large enough, say, the mass of a planet, the brightening lasts only a short time before fading again. By monitoring millions of distant stars and watching for these tiny flashes of magnified light, astronomers can infer the presence of otherwise invisible objects drifting between them. And when they began using this method seriously, something unexpected appeared. There were more rogue planets than anyone anticipated. Some early studies suggested there might be billions of them scattered across the Milky Way. In fact, the number of rogue planets might rival the number of stars in the galaxy. That means that for every glowing sun you see in the night sky, there may be at least one lonely world wandering the darkness between them. Perhaps more. Just imagine that for a moment. The Milky Way contains hundreds of billions of stars. Between them could drift an equally vast population of dark, cold planets, moving slowly through interstellar space. Entire worlds travelling alone. Some might be rocky like Earth. Others could be gas giants larger than Jupiter. Still others might be icy bodies the size of Neptune or Uranus. And because they formed in different star systems under different conditions, no two rogue planets are likely to be exactly the same. Some may have once been warm worlds orbiting close to their stars before being thrown outward by gravitational chaos. Others may have formed in colder regions and never known warmth at all. Some might even carry moons with them, little companions still orbiting faithfully as their parent planet drift through the galaxy. The thought of a planet wandering through deep space might sound impossibly cold and lifeless, but interestingly enough, not all rogue planets are necessarily frozen solid. A massive planet can generate internal heat through radioactive decay and residual energy left over from its formation. If it also possesses a thick atmosphere, that atmosphere can trap heat remarkably well. In fact, scientists have proposed that certain rogue planets could maintain subsurface oceans beneath thick layers of ice, warmed by geothermal heat from deep within their interiors. It's an intriguing possibility. A world drifting through the darkness, yet still harbouring liquid water beneath its frozen crust. No sunlight, no sunrise, just internal warmth and a quiet ocean sealed beneath miles of ice. Whether life could exist in such an environment remains an open question, but the idea reminds us that the universe often surprises us with unexpected possibilities. Still, most rogue planets are probably extremely cold places. Without a nearby star, surface temperatures can drop hundreds of degrees below freezing. Any atmosphere not tightly bound by gravity may slowly escape into space over millions of years. What remains is a dark world moving silently through the interstellar void, and yet, even in that darkness, the planet is not truly motionless. Everything in the galaxy is moving. Stars orbit the centre of the Milky Way. Nebulae drift and collapse. Clusters of stars pass near each other over millions of years. Rogue planets participate in that cosmic motion as well. Once ejected from their birth systems, they continue travelling through the galaxy along paths shaped by gravity. Occasionally they pass near other stars, their trajectories bending slightly as they move through the gravitational landscape of the Milky Way. Sometimes these encounters can even capture a rogue planet, pulling it into a new planetary system. In theory, a wandering world might spend millions of years alone before eventually becoming part of a completely different star system. But such captures are rare. Most rogue planets will wander for billions of years without ever settling down again. They simply drift, slowly crossing the immense distances between stars. To put those distances into perspective, consider our nearest stellar neighbour, Proxima Centauri. It lies about 4.24 light-years away from Earth. That's roughly 40 trillion kilometres. If a rogue planet were travelling through space at a typical interstellar speed, say around 20 kilometres per second, it would still take hundreds of thousands of years to cross the gap between two neighbouring star systems. Cosmic journeys are rarely quick. They unfold on timescales so long that entire civilizations might rise and fall before a wandering planet reaches its next destination. From that perspective, the idea of a rogue planet entering our solar system might seem incredibly unlikely, and in a sense it is. Space is vast, and the probability of a direct encounter with a massive wandering world is extremely small. Yet over the billions of years that the solar system has existed, such encounters may have happened before. Stars themselves pass relatively close to one another over cosmic timescales. Astronomers have identified several stars that came within a light-year or two of the Sun in the distant past. If those stars had planetary systems of their own, and many likely did, it's entirely possible that some wandering objects from those systems passed through our outer solar system long ago, perhaps unnoticed, perhaps leaving only subtle gravitational traces behind. Even today, the outermost regions of the solar system remain mysterious. The Oort cloud, a vast spherical halo of icy debris surrounding the Sun, may contain trillions of comet-like objects stretching tens of thousands of astronomical units into space. It represents the outer frontier of the Sun's gravitational influence. Beyond it lies interstellar space. That means a rogue planet drifting through the galaxy could, in theory, pass through the Oort cloud without ever coming anywhere near the inner planets. In such a scenario, the encounter might go almost completely unnoticed from Earth. But if the trajectory was slightly different, if the wandering planet's path carried it deeper into the solar system, then things could become much more interesting. Because gravity is not selective. Every massive object pulls on every other object nearby. Even a distant rogue planet would exert subtle forces on the outer edges of the solar system as it approached, and those forces would slowly begin to change things. Far out in the darkness beyond Neptune, small icy bodies would start to feel the disturbance first. Their quiet orbits, some unchanged for billions of years, might begin to shift. Tiny deviations at first, barely noticeable, but measurable. Astronomers watching those distant objects might start to notice unusual patterns emerging in their motions. A comet arriving earlier than predicted, a dwarf planet's orbit drifting slightly from its expected path. Subtle irregularities that suggest something massive is approaching from beyond the Sun's gravitational boundary. At that stage, the rogue planet would still be incredibly far away, too distant for the naked eye, too dim even for many telescopes, yet the solar system would already be responding to its presence. If a wandering planet were ever to appear on the outskirts of our solar system, one of the first questions astronomers would likely ask is a simple one. Where did it come from? Planets do not usually begin their existence alone. In most cases, they form around stars, inside vast rotating disks of gas and dust that surround young suns during their earlier stages. These disks are chaotic places, filled with swirling material, collisions, and powerful gravitational interactions that slowly assemble the building blocks of planetary systems. Our own solar system formed this way roughly 4.6 billion years ago. At the centre of a collapsing cloud of gas and dust, the Sun ignited, while the leftover material flattened into a spinning disk. Inside that disk, tiny particles began sticking together, gradually growing larger through countless collisions. Dust grains became pebbles, pebbles became rocks, rocks gathered into bodies kilometres across known as planetesimals. Over time, gravity took over as the dominant force, pulling these planetesimals together into larger and larger objects until full-sized planets began to emerge. But this process was anything but calm. Early planetary systems behave more like crowded construction zones than neatly arranged orbits. Newly forming worlds pull on one another constantly. Their gravitational fields tug and stretch surrounding material, nudging neighbouring objects into new paths. Sometimes those interactions are gentle, merely shifting a planet slightly closer or farther from its star. Other times, they are far more dramatic. To picture how a planet might become a cosmic runaway, imagine a system with several large planets forming around a young star. Each one follows its own orbit, but those orbits are not perfectly stable at first. Small gravitational influences accumulate over time, slowly changing the spacing between planets. Eventually, two planets may pass close enough that their gravitational fields interact strongly. When that happens, energy and momentum are exchanged between them. One planet might lose a bit of speed and settle into a tighter orbit around the star. The other might gain speed. If that extra speed becomes large enough, the second planet can be flung outward with such force that it escapes the star's gravitational grip entirely. At that moment, the planet transitions from a member of its system to a solitary traveller of the galaxy, a cosmic runaway. This process, known as gravitational scattering, is believed to be one of the most common ways rogue planets are created, and it likely happened frequently during the chaotic youth of planetary systems throughout the Milky Way. Even our own solar system may have experienced something similar long ago. In fact, modern models of the early solar system suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not always occupy the positions we see today. In their youth, they may have been packed closer together, interacting strongly with one another, and with countless smaller bodies in the surrounding disk. Over time, these interactions cause the planets to migrate outward and inward in a complex gravitational dance. Some smaller worlds may have been pushed completely out of the system. In other words, the solar system itself may have produced rogue planets during its earliest chapters. Those worlds would now be wandering somewhere in the galaxy, long separated from the star that once warmed them. But gravitational scattering is not the only path to planetary exile. Another possibility arises during close encounters between entire star systems. Stars do not remain perfectly isolated as they orbit the Milky Way. Over millions and billions of years, they occasionally pass relatively close to one another. These encounters are rarely dramatic collisions, since the distances between stars are enormous, but gravitational influences can still reach surprisingly far. Imagine two star systems drifting within a few trillion kilometers of each other. Each system carries its own planets, asteroids, and comet clouds. As the stars approach, their gravitational fields begin tugging on those distant objects. Planets in wide orbits around their stars are especially vulnerable to disruption during such encounters. A close, stellar flyby can distort those orbits dramatically. In some cases, the gravitational pull of the passing star may capture a planet from the other system. In other cases, the combined gravitational forces may simply fling the planet away from both stars entirely. When that happens, the result is another rogue planet launched into interstellar space by the gravitational interaction of two passing suns. This type of planetary exchange or ejection may have occurred many times throughout the galaxy's history. Star clusters, where hundreds or thousands of stars form relatively close together, are particularly active environments for such encounters. In those crowded stellar nurseries, gravitational interactions between neighbouring systems are far more common than they are in the relatively quiet region of the galaxy where our Sun now resides. During the early stages of a star cluster's life, entire planetary systems may be reshaped by these interactions. Some planets may be captured by new stars, others may be cast out entirely. The galaxy is a busy place when seen on long enough timescales. Yet there is another pathway by which rogue planets might come into existence, and this one is perhaps even more surprising. Some planets may never have belonged to a star at all. Under the right conditions, a cloud of gas in space can collapse directly into a planetary mass object without ever igniting nuclear fusion. In other words, a planet-sized body may form in isolation, much the way a star does, but without enough mass to begin the nuclear reactions that cause stars to shine. These objects blur the line between planets and very small stars known as brown dwarfs. Brown dwarfs occupy a strange middle ground between planets and stars. They are massive enough to generate a small amount of heat through gravitational compression, but not massive enough to sustain the long-term fusion that powers stars like the Sun. Some rogue planets detected by astronomers may actually be extremely small brown dwarfs formed in this way. Others appear to have masses more typical of planets formed in disks around stars. In practice, distinguishing between these origins can be difficult, especially when observing distant objects drifting alone through space. Regardless of how they formed, rogue planets share a common fate. They travel. Once freed from their birth systems, these worlds move through the galaxy along paths determined by the gravitational landscape of the Milky Way. The galaxy itself rotates slowly, carrying stars, nebulae, and rogue planets alike along enormous orbital paths around its central core. From the perspective of a rogue planet, the galaxy becomes its new environment. It may pass near distant stars over millions of years, feeling their faint gravitational tugs as it continues its journey. Occasionally, those encounters may alter its path slightly, but most of the time the rogue planet simply drifts onward through vast stretches of empty space. The scale of that emptiness is difficult to imagine. The nearest star to our Sun lies more than 4 light-years away. Between those two stars is a region so empty that a wandering planet could travel for hundreds of thousands of years without coming close to anything at all. Yet even in that emptiness, gravity continues shaping trajectories. Stars orbit the galactic center. Dark matter influences the motion of entire star systems, and rogue planets move through that environment like slow travelers crossing a nearly infinite desert. Their journeys may last billions of years. Some may eventually pass near another star system. In rare cases, they might be captured into new orbits, becoming adopted members of entirely different planetary families. More often, they simply pass through, their paths bending slightly as they move past distant stars before continuing onward into the darkness. If one of those wandering worlds happened to approach our solar system, it would not arrive suddenly or violently. Instead, it would appear gradually. First as a distant gravitational influence far beyond Neptune, then as a faint object slowly creeping inward through the outer reaches of the Sun's domain. Its speed would depend on its original trajectory and on the gravitational forces it encounters along the way. Typical rogue planets move through the galaxy at tens of kilometers per second relative to nearby stars. That may sound incredibly fast, but on cosmic scales it still means that travel takes a very long time. A rogue planet approaching from the outer edge of the Oort cloud could take tens of thousands of years to reach the region of the giant planets. From Earth's perspective, the approach would unfold across generations. Astronomers might first notice subtle gravitational disturbances among distant cometary objects. Years later, telescopes might detect a faint moving point of reflected sunlight. Decades after that, detailed orbital calculations would begin revealing how the wandering world might interact with the planets already orbiting the Sun. All of that would happen long before the planet came anywhere near the inner solar system, because the Sun's gravitational influence stretches extremely far outward. Any object entering that region begins feeling the Sun's pull long before reaching the familiar planetary orbits we often picture when thinking about the solar system. In effect, the rogue planet would gradually transition from being an interstellar traveller to a temporary visitor within the Sun's vast gravitational domain. And as it did, every planet already orbiting the Sun would begin to feel the newcomer's presence. At first, those influences would be subtle, tiny shifts in the motion of distant bodies, small deviations in the long paths of comets at the solar system's edge. But gravity has a way of spreading its influence outward, like ripples across a quiet pond. The closer the rogue planet moved toward the Sun, the stronger those ripples would become. Once a planet has been thrown free from the gravitational hold of its star, its journey enters a very different phase. The violent moment of escape might last only hours or days, a sudden burst of acceleration caused by a close gravitational encounter with another planet or passing star. After that brief drama fades, the runaway world settles into something much quieter. It begins to drift. There is no star to orbit anymore, no bright sun dominating the sky, no regular cycle of days and nights. Instead, the planet travels through the enormous regions of space that lie between stellar systems. Astronomers call this environment interstellar space, and while that phrase might sound dramatic, the reality of it is surprisingly simple. It is mostly empty. If you could somehow stand on the surface of a rogue planet wandering through that darkness, the sky would look very different from the one we see on Earth. Here, our night sky is filled with countless stars, each one a distant sun shining through the clear black of space. Even with the naked eye, thousands of stars can be seen under ideal conditions, and with telescopes, millions more appear. But from the deep void between stars, the sky would be far more sparse. Most stars would appear faint and widely scattered, tiny points of light separated by enormous distances. The nearest sun might be several light years away, glowing softly like a distant lantern across a vast plain. Its light would provide almost no warmth, only a faint glimmer against the darkness. Without a nearby star dominating the sky, there would be no sunrise, no sunset, just a slow-turning planet beneath a quiet canopy of distant starlight. The silence of that environment is difficult to imagine, because everything about it operates on scales far beyond human experience. Even the emptiness itself has numbers attached to it. Interstellar space contains a few stray atoms of hydrogen here and there, perhaps one atom per cubic centimetre on average. That might sound like something, but compared to the air around us on Earth, which contains trillions upon trillions of atoms in the same volume, interstellar space is extraordinarily thin. A better comparison might be this. If you took the best vacuum chamber ever built in a laboratory on Earth and removed nearly every particle from inside it, interstellar space would still be emptier. In such a place, there is nothing to slow a wandering planet down. Once it begins moving, it keeps moving. Gravity still shapes its path, of course. The galaxy itself contains hundreds of billions of stars, along with vast clouds of gas and invisible halos of dark matter. All of these contribute to the gravitational structure of the Milky Way, guiding the motion of objects within it. A rogue planet follows that invisible gravitational map as it travels. From a distance, its path might appear almost straight, but over millions of years, the planet's trajectory gradually curves as it orbits the center of the galaxy, along with everything else nearby. The Sun itself is doing the same thing. Right now, our entire solar system is moving through the Milky Way at roughly 220 kilometers per second, completing one full orbit around the galaxy about every 230 million years. Every planet, asteroid and comet travelling with the Sun shares that motion. Rogue planets participate in the same galactic journey, except they are not tied to any single star. Instead, they move independently, tracing their own paths through the galaxy's gravitational field. Some might wander through relatively quiet regions for billions of years without coming anywhere near another star system. Others might pass close enough to distant stars that their trajectories bend slightly, the gentle tug of gravity nudging them onto new courses through space. Those encounters are usually subtle. The distances between stars are so large that even when two stars pass close to each other in cosmic terms, they may still be separated by trillions of kilometers. Yet gravity is patient. Given enough time, even weak gravitational interactions can alter a wandering planet's direction. Over millions of years, those tiny adjustments accumulate. A rogue planet might start its journey moving in one direction across the galaxy, only to find its path slowly reshaped by the combined influence of nearby stars and galactic gravity. The result is a slow, wandering migration through the Milky Way. For the planet itself, however, the environment remains largely unchanged. Darkness dominates. The only significant sources of energy come from within the planet itself. Most planets begin their lives extremely hot. During formation, the countless collisions that build a planet generate enormous amounts of heat. That heat becomes trapped inside the growing world, creating molten interiors and volcanic activity that can last for millions or even billions of years. On Earth, much of that internal heat still remains today. The movement of tectonic plates, the eruption of volcanoes, and the circulation of magma beneath the crust are all reminders that our planet's interior is still warm. For a rogue planet drifting through interstellar space, internal heat becomes especially important. Without a nearby star to provide sunlight, the surface temperature would drop dramatically. Any atmosphere not tightly bound by gravity might slowly escape into space, and oceans exposed to the surface would likely freeze solid. Yet beneath the surface, things could remain surprisingly active. A large enough planet can retain heat for billions of years, particularly if it contains radioactive elements such as uranium and thorium within its interior. The slow decay of those elements releases energy, helping maintain warmth deep inside the planet. If the planet also possesses a thick insulating atmosphere, that internal heat might be trapped effectively enough to create interesting environments beneath the surface. Scientists have suggested that some rogue planets could maintain subsurface oceans hidden beneath thick ice layers, similar to the suspected oceans beneath the icy crusts of moons like Europa or Enceladus in our own solar system. In those environments, liquid water could persist far from any star. Life, if it ever emerged under such conditions, would rely not on sunlight, but on chemical energy and geothermal heat. It's a fascinating possibility, though one that remains purely theoretical for now. Most rogue planets are probably much colder and quieter places. Their surfaces frozen, their skies black, their landscapes illuminated only by distant starlight. But even in such stillness, time continues passing. Years go by as the planet rotates slowly in the darkness. Centuries pass as it travels across the galaxy. Millennia slip past as its trajectory carries it through the vast corridors between stars. Eventually, the wandering world might encounter something that alters its journey. Perhaps it drifts near a passing star, its path bending slightly under the star's gravitational influence. Perhaps it passes through the outer regions of a planetary system, disturbing distant comets before continuing onward again. Or perhaps, by coincidence, its path intersects with the enormous gravitational boundary surrounding a star like our Sun. Every star possesses such a boundary. The Sun's gravitational influence stretches far beyond the familiar orbits of the planets. Even distant objects in the Oort cloud, tens of thousands of astronomical units from the Sun, remain loosely bound to it. Astronomers sometimes refer to this region as the Sun's gravitational sphere of influence, or more formally, the Hill sphere of the solar system relative to the surrounding galaxy. A rogue planet approaching this region would gradually begin feeling the Sun's pull. At first, the effect would be extremely small. The planet would still behave mostly like an interstellar traveller, moving along its galactic path. But as it drifted closer, the Sun's gravity would begin bending that path slightly inward. This transition could take thousands of years. From the rogue planet's perspective, nothing dramatic would happen immediately. Its motion would simply curve ever so slightly toward the Sun as it entered the outermost boundaries of the solar system. But from the perspective of the solar system itself, something subtle would begin unfolding. The outer Oort cloud, filled with trillions of icy bodies left over from the solar system's formation, would experience the first disturbances. Those objects orbit the Sun in extremely wide paths that can take millions of years to complete. Their orbits are fragile. easily perturbed by passing stars or distant gravitational influences. A rogue planet drifting through that region would introduce a new gravitational force into an already delicate environment. Some comets might have their orbits nudged inward, others might be flung outward, escaping the solar system entirely. Still others might shift just enough that their distant journeys eventually bring them toward the inner solar system tens of thousands of years later. Astronomers might notice these subtle changes long before the rogue planet itself becomes visible. Unusual clusters of incoming comets, slight distortions in the distribution of distant icy bodies, tiny irregularities in orbital calculations that had previously matched observations perfectly. Such clues might be the first hints that something massive is approaching from the darkness between stars. But at that stage, the wandering planet would still be incredibly far away, too dim for most telescopes, too distant to have any noticeable effect on the familiar planets closer to the Sun. Yet its slow approach would continue, year after year, century after century, gradually leaving the vast silence between stars behind as it moves deeper into the outermost edges of our solar system. And as it does, the distant frontier where the Sun's influence begins to compete with the rest of the galaxy will become the stage for the first measurable changes. When we imagine a rogue planet entering the solar system, it's easy to picture something dramatic. A dark world suddenly appearing in the sky, astronomers sounding alarms, telescopes swinging into position across the globe. Reality, however, tends to unfold much more quietly. Space is large beyond ordinary comprehension, and objects moving through it rarely arrive with much fanfare. A wandering planet approaching our solar system would begin its journey into the Sun's territory from incredibly far away, in regions so distant that even our most powerful telescopes struggle to see clearly. Which naturally leads to a question that scientists have asked many times. Could one already be on its way, not racing toward us in some catastrophic scenario, but simply drifting through the galaxy along a path that happens to intersect the outskirts of our solar system? The answer is both reassuring and intriguing. Astronomers cannot rule out the possibility entirely, but if such an object exists, it would almost certainly be extremely far away right now. To understand why, it helps to consider how scientists search for distant objects in the first place. Unlike stars, which generate their own light through nuclear fusion, planets shine only by reflecting the light of nearby stars. The farther a planet is from a star, the dimmer it appears. A rogue planet travelling through interstellar space has no bright sun to illuminate it. That makes it exceptionally difficult to detect. In fact, if a planet the size of Earth were currently drifting through the outermost regions of the solar system, tens of thousands of astronomical units away, it might be so faint that even large telescopes would struggle to see it directly. Fortunately, astronomers have developed several clever methods for discovering distant objects that cannot easily be seen. One of the most important approaches involves carefully studying the motion of known objects. In a gravitational system like our solar system, everything moves in predictable ways. Planets follow well-understood orbits around the Sun, and even small bodies like asteroids and comets trace paths that can be calculated with remarkable precision. If something large and unseen enters the region, its gravity subtly alters those motions. Think of it like a pond filled with floating leaves. If a large object moves beneath the surface, the water ripples slightly, causing the leaves to drift in new directions. Even if you cannot see the object itself, the pattern of ripples might reveal that something is passing underneath. Astronomers use a similar strategy. They track the positions of distant objects over time, looking for tiny deviations from their expected orbits. If enough of those deviations appear, scientists begin asking whether an unseen mass might be responsible. This exact approach led to the discovery of Neptune in 1846. At the time, astronomers noticed that Uranus was not moving exactly as predicted by existing calculations. Two mathematicians working independently proposed that another planet farther from the Sun might be tugging on Uranus with its gravity. When telescopes were pointed toward the predicted location, Neptune was found almost exactly where the equation said it should be. It was one of the great triumphs of celestial mechanics. Even today, astronomers continue using this method to search for unseen objects in the outer solar system. You may have heard of the hypothetical Planet 9, a proposed large planet that could be lurking far beyond Neptune. The idea emerged when researchers studying distant icy bodies noticed that several of them followed strangely aligned orbits. One possible explanation is that a massive unseen planet is influencing those objects from afar. Whether Planet 9 truly exists remains an open question, but the investigation illustrates how astronomers search for hidden gravitational influences in the solar system. If a rogue planet were approaching from interstellar space, its gravity might eventually produce similar clues. Objects in the outer solar system would begin drifting slightly from their predicted paths. Cometary orbits might change. Clusters of distant bodies might show unexpected alignments. These changes would likely appear very gradually. The outer solar system is vast and gravitational disturbances weaken rapidly with distance. A rogue planet would need to move relatively close, on astronomical scales, before its influence became noticeable. Even then, detecting it would require years of careful observation. Fortunately, modern astronomy is remarkably well equipped for this task. Across the world and in orbit above Earth, telescopes constantly scan the sky for faint moving objects. Surveys like Pan-STARRS in Hawaii and the Vera C. Rubin Observatory in Chile monitor large portions of the sky repeatedly, searching for asteroids, comets, and other distant bodies. These surveys generate enormous data sets, capturing images of the night sky night after night. Computers compare those images, identifying objects that move slightly against the background of distant stars. Most of the moving points of light they find turn out to be familiar objects, asteroids in the inner solar system or comets from the outer regions. Occasionally, however, astronomers discover something entirely new. In 2017, for example, scientists detected a mysterious object passing through the solar system on a highly unusual trajectory. It was named Oumuamua, a Hau'oumuamua, a Hawaiian word meaning scout or messenger from afar. Unlike ordinary asteroids or comets, Oumuamua did not originate within the solar system. Its trajectory showed that it had arrived from interstellar space, passed near the Sun, and was now leaving again. It was the first known visitor from another star system ever detected travelling through our cosmic neighbourhood. Just 2 years later, another interstellar object appeared, a comet named 2I/Borisov, discovered by amateur astronomer Gennady Borisov. Unlike Oumuamua, which behaved somewhat strangely, Borisov looked more like a typical comet, complete with a glowing coma and tail as it approached the Sun. These discoveries confirmed something astronomers had long suspected. Interstellar objects do occasionally pass through the solar system. Most of them are probably small, asteroids or comets rather than full-size planets, but their presence demonstrates that the boundaries between star systems are not perfectly sealed. The galaxy is full of wandering debris. Planets, being much larger, would be far rarer visitors. Yet the principle remains the same. Given enough time, even unlikely encounters can happen. Still, if a rogue planet were currently approaching the solar system, astronomers would likely detect signs of it long before it reached the inner regions. Large objects reflect more light than small ones, making them easier to spot once they enter the range of modern telescopes. Even if the planet were extremely dark, its motion against the background stars would eventually reveal its presence. Astronomers also search the sky in infrared wavelengths, which detect heat rather than visible light. Rogue planets that retain internal warmth may glow faintly in infrared, allowing space-based telescopes to detect them even when they reflect a little sunlight. The WISE Space Telescope, for example, conducted a detailed infrared survey of the entire sky, looking for brown dwarfs and other faint objects near the Sun. Its observations place strong limits on the existence of undiscovered massive planets, in our immediate cosmic neighbourhood. The results were reassuring. No large rogue planets appear to be lurking within the inner regions of the solar system. But beyond that, far beyond Neptune and the Kuiper Belt, there remains a tremendous volume of space where objects could still hide. The Oort cloud extends tens of thousands of astronomical units from the Sun. At those distances, even a large planet could remain extremely faint. If a rogue planet were currently drifting somewhere out there, it might still take thousands of years before it approached close enough for astronomers to detect it clearly. Which means that while we have no evidence of a rogue planet currently heading toward us, the possibility cannot be completely ruled out. Not because scientists are missing something obvious, but because the outer solar system is simply so vast. It takes time for wandering objects to reveal themselves, and time is something the universe has in abundance. If such a planet were indeed on its way, the first hints would likely appear not as dramatic discovery, but as small irregularities in the motions of distant objects. Astronomers would notice, calculations would be checked, new observations would be made. Slowly, a picture would begin forming of a massive object approaching from the darkness beyond the Sun's known frontier. At first, it would remain just a faint point moving slowly against the starry background. But as the years passed, that point would grow brighter, its path would become clearer, and eventually scientists would realize that the solar system had acquired an unexpected visitor. One that had spent perhaps billions of years wandering between stars before finally arriving at the edge of our Sun's domain. Long before anyone on Earth would see a rogue planet in the sky, the solar system itself would begin to react to its presence, not with sudden violence or dramatic collisions, but with small, quiet changes that astronomers would notice only after careful measurement and patient observation. The solar system is often imagined as a collection of planets circling the Sun in simple paths, but in reality it is a remarkably delicate gravitational system. Every object exerts a pull on every other object. The Sun dominates, of course, holding the planets in orbit with its enormous gravity, but the planets themselves also tug on one another in subtle ways. These interactions are so predictable that astronomers can calculate planetary positions decades or even centuries into the future with extraordinary precision. When something changes those calculations, scientists notice. That is exactly how Neptune was discovered in the 19th century. The orbit of Uranus showed slight irregularities that could not be explained by known planets. Mathematicians studied the problem, predicted the position of a new planet, and when telescopes looked in that direction, Neptune appeared almost exactly where the equations suggested. It was one of the earliest demonstrations that unseen objects could reveal themselves through gravity alone. If a rogue planet were approaching our solar system from interstellar space, something similar would likely happen again. But the first disturbances would not involve the familiar planets like Mars or Jupiter. Those worlds are relatively close to the Sun, tightly bound within stable orbits shaped by billions of years of gravitational interactions. Instead, the earliest signs would appear far beyond them, in the outermost regions where the Sun's gravitational hold becomes weaker and more fragile. Out there lies the Oort cloud, a vast spherical region filled with icy remnants left over from the formation of the solar system. These objects are ancient, some of them dating back to the earliest days when planets were still assembling from dust and rock. The Oort cloud may contain trillions of comet-like bodies spread across distances tens of thousands of times greater than the distance between Earth and the Sun. At those distances, the Sun appears only slightly brighter than the other stars in the sky. The gravitational grip holding those distant objects in orbit is gentle, almost tentative. Because of that, the Oort cloud is extremely sensitive to outside influences. Passing stars, for example, occasionally disturb it. When a star drifts within a few light years of the Sun, its gravity can slightly alter the paths of distant comets. Some of those comets may then begin long journeys inward toward the inner solar system, eventually appearing in our skies thousands or even millions of years later. A rogue planet entering this region would produce a similar disturbance. Its gravity would begin tugging on nearby icy bodies, shifting their orbits in small but measurable ways. Some objects might be nudged inward, beginning slow descents toward the Sun. Others might be flung outward, escaping the solar system entirely. These changes would happen gradually. A comet's orbit might shift by a tiny fraction of a degree. A distant object's predicted position might differ from observations by a small but persistent amount. At first, astronomers studying these objects might assume that measurement errors or incomplete orbital data were responsible. After all, tracking bodies so far away is challenging. Many Oort cloud objects have orbital periods measured in millions of years, and their paths are often calculated from only brief observations. But if multiple objects began showing unusual motions at the same time, curiosity would grow. Researchers would begin comparing notes. New telescopes might be pointed toward the regions where these disturbances seemed strongest. Data from sky surveys would be reanalyzed. Over time, a pattern might emerge. If the disturbances appeared to radiate outward from a particular direction in space, scientists might suspect that something massive was approaching from that region. Not yet visible, but already influencing the solar system through gravity. Such discoveries rarely happen overnight. Astronomy often progresses through small steps, each new observation adding a little more clarity to the picture. Years might pass as researchers debate possible explanations for the unusual motions. Some might suggest that the disturbances are caused by previously unknown populations of distant objects interacting with one another. Others might propose that measurement errors are being misinterpreted as real effects. But if the gravitational anomalies continued appearing consistently, attention would gradually focus on the possibility of an unseen massive object moving inward. The search for that object would begin in earnest. Large telescopes would scan the sky in the suspected direction, looking for faint points of light moving slowly against the background of distant stars. Observatories specializing in infrared wavelengths might join the effort, since a rogue planet could still emit faint heat from its interior even without sunlight warming its surface. Detecting such an object would still be difficult. At enormous distances from the Sun, even a large planet reflects very little light. Against the blackness of space, it might appear no brighter than a tiny moving speck in telescope images. Yet astronomers are patient observers. They routinely track objects millions of times dimmer than what the human eye can see. With enough data, even a faint moving point can eventually be identified and followed. Once detected, scientists would begin calculating its trajectory. This process would involve carefully measuring the object's position over many nights, and comparing those measurements with models of how gravity should influence its motion. From those calculations, astronomers could determine several key properties of the visitor: its approximate mass, its speed relative to the Sun, and most importantly, its path through the solar system. At this stage, the rogue planet would still be extremely far away, perhaps thousands of astronomical units from the Sun. From Earth, it would remain invisible without powerful telescopes. But scientists would already know something important. The solar system had acquired a visitor. The next question would naturally be how close that visitor might come. Many possible outcomes would exist depending on the planet's speed and trajectory. In the most benign scenario, the rogue planet might pass through the outer regions of the solar system without ever approaching the inner planets. Its gravity would disturb some distant comets and perhaps slightly alter the orbits of a few outer objects before it continued its journey back into interstellar space. Such an event might unfold quietly over tens of thousands of years. Human civilization might record the discovery, study the visitor for generations, and watch it slowly fade into the darkness again. But other possibilities could be more complicated. If the rogue planet's path brought it closer to the giant planets, Jupiter, Saturn, Uranus, or Neptune, the gravitational interactions between those massive worlds could become significant. Planets are not small objects. Jupiter alone contains more than twice the mass of all the other planets combined. When such enormous bodies interact gravitationally, they can exchange energy in ways that alter orbital paths over long periods of time. Even a relatively distant encounter between two massive planets can shift their trajectories slightly. Those shifts might not be dramatic immediately, but over thousands or millions of years, they can reshape the architecture of an entire planetary system. This is one reason astronomers would pay extremely close attention to the rogue planet's path. Computer simulations would run continuously, exploring millions of possible trajectories and calculating how the solar system might respond. Supercomputers would simulate gravitational interactions between the visitor and every major planet, asteroid belt object, and distant comet cloud. Most of those simulations would probably show minimal effects. The solar system has survived countless disturbances over billions of years and remains remarkably stable. But a few scenarios might reveal more dramatic possibilities. And while scientists work through those calculations, the rogue planet itself would continue its slow inward drift. Year by year, it would move slightly closer to the Sun. Decade by decade, it would grow a little brighter in telescope images. Eventually, after many years of observation, its orbit would become well understood. Astronomers would know whether it would pass safely through the outer regions or venture deeper into the solar system. At that point, the wider public would likely hear about it. News headlines might describe the discovery of a mysterious wandering planet approaching from interstellar space. Artists would begin illustrating what such a world might look like. Scientists would explain that there was no immediate danger, but that the event offered a rare opportunity to observe a rogue planet up close. For most people on Earth, life would continue normally. The sun would rise each morning. Cities would move through their daily rhythms. But somewhere in the outer solar system, a distant traveller would be moving slowly closer to the realm of the planets. By the time astronomers were certain that a rogue planet was approaching the solar system, the object itself would still be unimaginably far away. Even with the most powerful telescopes, it would likely appear as nothing more than a dim point moving slowly against the background of distant stars. But distance does not prevent gravity from doing its work. Gravity travels across space without hesitation. It does not weaken suddenly or switch on at a particular boundary. Instead, it fades gradually with distance, its influence stretching outward across enormous regions of space like the gentle pull of a tide spreading across an ocean. And so, even when the wandering planet remained far beyond the familiar planets of our solar system, its presence would already be felt. Not strongly, not violently, just quietly. The first stage of that influence might be described almost as a whisper in the language of celestial mechanics. Objects at the outer edge of the sun's domain would begin to feel an additional gravitational pull layered on top of the sun's own attraction. The Oort cloud, that vast halo of icy bodies surrounding the solar system, would again be the earliest region to respond. These objects orbit so far from the sun that their motions are already extremely slow and delicate. Some of them take millions of years to complete a single journey around the sun. When the rogue planet's gravity reached them, it would begin altering those ancient paths in subtle ways. A comet drifting through the outer cloud might feel a slight tug that changes its direction by only a tiny amount. That small adjustment could send it onto a new orbit that slowly carries it inward toward the sun. Another icy body might receive a nudge in the opposite direction, gaining enough speed to escape the sun's gravitational influence entirely. In this way, the rogue planet's arrival would gradually stir the quiet outskirts of the solar system. From Earth, those disturbances might appear years or decades later as a small increase in the number of long-period comets entering the inner solar system. Astronomers would notice that something was shifting the delicate gravitational balance at the solar system's frontier, but the rogue planet itself would still be many thousands of astronomical units away. The whisper of its gravity would continue spreading inward. Far beyond the orbit of Neptune lies another region filled with icy remnants from the solar system's formation, the Kuiper Belt. This flattened disk of objects contains dwarf planets like Pluto, along with countless smaller bodies slowly circling the Sun. Unlike the Oort cloud, whose objects move in every direction, the Kuiper Belt lies roughly in the same plane as the planets. Its inhabitants follow predictable paths shaped by the gravity of the giant planets, particularly Neptune. Because of that relationship, the Kuiper Belt acts almost like a sensitive gravitational instrument. When something alters the balance of forces in the outer solar system, the objects within this region can reveal the disturbance. As the rogue planet continued its slow approach, some Kuiper Belt objects might begin drifting slightly from their expected positions. These deviations would not be dramatic. Imagine a distant object that normally completes an orbit in a few hundred years. A small gravitational tug might alter its orbit just enough that its predicted position shifts by a fraction of a degree. At first, such changes might seem insignificant. Astronomers tracking distant objects often deal with uncertainties in measurements. Observations separated by years or decades can produce small discrepancies that are usually resolved with improved data. But if the rogue planet's influence continued growing, more objects would begin showing similar deviations. The pattern would become harder to ignore. Researchers might notice that the disturbances appear strongest in a particular region of the sky, corresponding to the direction from which the rogue planet was approaching. Computer models would attempt to reproduce the observed motions. If those models consistently pointed to the gravitational influence of a large unseen object moving inward, confidence in the rogue planet's existence would grow stronger. Yet even then, the situation would remain calm on human timescales. The distances involved are simply too vast for anything to happen quickly. Suppose the rogue planet were travelling through the outer solar system at a typical interstellar speed of 20 kilometers per second. That may sound incredibly fast, but even at that velocity it would take decades or centuries to move across the immense gap between the Oort cloud and the region of the giant planets. During that time, the gravitational influence of the wandering world would continue spreading inward. Like a slow ripple moving across a lake, the disturbance would gradually reach objects closer to the Sun. Neptune, the most distant of the major planets, would eventually begin to feel it. Neptune orbits the Sun at an average distance of about 30 astronomical units, taking roughly 165 Earth years to complete a single revolution. Its motion is remarkably stable, guided by the Sun's gravity and subtly influenced by the other giant planets. But even small disturbances in the outer solar system can slightly alter Neptune's orbit. These changes would likely appear first in the form of tiny variations in its orbital parameters. Astronomers might notice that Neptune's position differs from predictions by small but measurable amounts. Such discrepancies would not be immediately alarming. Planetary orbits are affected by many influences, including gravitational interactions with other planets and the cumulative effects of small bodies in the solar system. However, if Neptune's deviations match the expected gravitational influence of the approaching rogue planet, the case would become increasingly convincing. The giant planet itself would continue following its path around the Sun, but the shape of that path might shift slightly over time. A minute change in orbital speed, a small alteration in the tilt of the orbit, tiny adjustments that could only be detected through careful measurements spanning years or decades. For astronomers studying planetary motion, such shifts would be deeply interesting. They would provide direct evidence that the solar system's architecture was responding to the presence of an incoming massive object. At this stage, however, the rogue planet would still remain far from the inner solar system. From Earth's perspective, nothing unusual would be visible in the sky. No new star-like object would appear to the naked eye. No sudden celestial event would capture public attention. The Sun would continue rising and setting exactly as it always had. The Moon would follow its familiar cycle of phases. The planets would shine in their usual places among the stars. Yet in the quiet mathematics of celestial mechanics, something new would be unfolding. Astronomers would refine their models again and again as new observations arrived. Each year of data would sharpen their understanding of the rogue planet's trajectory and its potential influence on the solar system. Simulations might explore a wide range of possible outcomes. Some scenarios would show the wandering planet passing safely through the outer regions, without ever coming close to the giant planets. Others might reveal more interesting possibilities. Because if the rogue planet's path eventually brought it near Neptune or Uranus, the gravitational interaction between those worlds could become far more significant. Planetary encounters do not require direct collisions to produce dramatic results. Even a relatively distant flyby between two massive bodies can alter their orbits in ways that echo throughout the solar system. Gravity exchanges energy between objects like an invisible currency. A planet passing near another planet may speed up or slow down slightly, changing the size or shape of its orbit around the Sun. These changes are usually small, but over long periods they can accumulate. In the early history of the solar system, such gravitational interactions reshape the orbits of the giant planets themselves. Scientists believe that Jupiter and Saturn once migrated through the solar system in response to interactions with surrounding debris and smaller bodies. Those migrations helped scatter countless asteroids and comets into new orbits, shaping the structure of the solar system we see today. If a rogue planet entered the region of the giant planets, something similar could happen again, though the exact outcome would depend heavily on the visitor's mass and trajectory. At the moment when Neptune first began feeling the whisper of the rogue planet's gravity, none of that would be certain yet. The wandering world would still be far away, its path continuing slowly inward through the outer solar system. But with every passing year, the gravitational influence of that traveller would grow stronger, and eventually the quiet whispers felt by distant objects would become more noticeable. For most of the solar system's history, Neptune has occupied a quiet and distant position at the edge of the planetary family. Orbiting far beyond the warm inner regions where sunlight is strong and familiar, it moves slowly around the Sun in a wide, steady path that takes 165 Earth years to complete. From our perspective on Earth, Neptune feels remote and calm. It appears as a faint bluish point in telescopes, a cold gas giant bathed in weak sunlight nearly 30 times farther from the Sun than we are. Yet Neptune is not just a quiet observer. It plays a crucial role in shaping the outer solar system. Its gravity helps control the motions of countless icy bodies in the Kuiper Belt. Some objects become trapped in orbital resonances with Neptune, meaning they complete a certain number of orbits around the Sun for every orbit Neptune makes. Pluto, for example, follows a 3-to-2 resonance with Neptune, completing 2 trips around the Sun for every 3 of Neptune's. This arrangement prevents the two worlds from ever colliding, despite their paths occasionally bringing them close together. It is a delicate gravitational choreography that has persisted for billions of years. But if a rogue planet were approaching the solar system from the darkness between stars, Neptune would likely be the first of the major planets to feel its influence in a meaningful way. Not immediately and not dramatically at first. Instead, the change would begin almost invisibly. Astronomers track the positions of planets with extraordinary precision. Neptune's orbit is known so well that even tiny deviations from its predicted path can be detected through careful observations. These measurements involve sophisticated techniques, including radio signals sent to distant spacecraft and detailed monitoring of planetary positions against background stars. If the rogue planet moved close enough to the outer solar system, Neptune's motion might begin showing very slight discrepancies. Perhaps the planet would arrive at a certain point in its orbit a few seconds earlier or later than expected. Perhaps the tilt of its orbital path would shift by a tiny fraction of a degree. Individually, such changes might seem insignificant, but when compared to decades of precise observations, they would stand out. Astronomers studying Neptune might notice that their models of its motion no longer fit the data perfectly. Small corrections would be attempted at first, accounting for gravitational influences from other known planets. But if those adjustments fail to explain the discrepancies, attention would turn toward the approaching rogue planet. Computer simulations would begin incorporating the visitor's estimated mass and trajectory, allowing scientists to predict how its gravity should influence Neptune over time. If the models matched the observations, the conclusion would become difficult to ignore. The outermost giant planet had begun responding to the presence of an interstellar intruder. From Neptune's perspective, the rogue planet would still be far away, perhaps several astronomical units beyond its orbit. But even at those distances, the gravitational pull of a planet-sized object can subtly alter orbital motion. This is because gravity does not operate in isolation. Every object in the solar system contributes to a constantly shifting network of forces. The Sun provides the dominant pull, but the planets also interact with one another, exchanging tiny amounts of energy as they move along their paths. Introduce a new massive body into that system, and the balance begins to shift. Neptune's orbit might stretch slightly in one direction and compress in another. Its speed around the Sun might change by a small amount. Even the timing of its seasonal cycles, already unimaginably long by human standards, could drift slightly as its orbit adjusts. None of this would be noticeable to anyone standing on Earth and looking at the night sky. Neptune is far too distant to reveal such changes visually. But within the calculations of astronomers, the differences would be unmistakable. At the same time, Neptune's moons would also begin responding to the altered gravitational environment. The planet's largest moon, Triton, follows a unique orbit unlike that of any other large moon in the solar system. Triton moves in a retrograde orbit, meaning it travels around Neptune in the opposite direction of the planet's rotation. Scientists believe Triton was once an independent object in the Kuiper Belt that was captured by Neptune long ago. Its unusual orbit makes it particularly sensitive to gravitational disturbances. If Neptune's motion changed even slightly, Triton's orbit might shift as well. The Moon might move slightly closer to Neptune or drift a little farther away, depending on how the gravitational balance evolved. These effects would likely remain small, but they would add further evidence that the outer solar system was experiencing a new influence. Meanwhile, the rogue planet itself would continue its slow inward journey. Over years and decades, it would move closer to Neptune's orbital distance, growing gradually brighter in telescope images as it reflected more sunlight. Astronomers would refine their estimates of its size and mass. If the object were comparable in size to Neptune itself, its gravitational effects would be considerable. If it were smaller, perhaps the mass of Earth or Mars, the disturbances would be weaker but still measurable. Every new observation would feed into updated simulations. Scientists would explore countless possible future scenarios, examining how the rogue planet might interact with Neptune and the other giant planets as it approached. Most simulations would likely show relatively mild outcomes. In many cases, the rogue planet might pass through the outer solar system without ever coming dangerously close to the major planets. Its gravitational influence would temporarily disturb Neptune's orbit before fading as the visitor continued its journey back into interstellar space. But other scenarios might be more complex. Planetary encounters can behave in surprising ways. If the rogue planet's trajectory carried it near Neptune, the two worlds could engage in a gravitational exchange of energy. This process, sometimes called a gravitational slingshot, occurs when two massive bodies pass near each other and transfer momentum through their gravitational interaction. Space agencies have used this technique for decades to accelerate spacecraft. By flying close to planets like Jupiter or Saturn, probes can gain speed and change direction without using additional fuel. A similar effect can occur naturally between planets. If the rogue planet passed close enough to Neptune, one of the two worlds might gain energy while the other loses it. In one scenario, the rogue planet might be flung outward again, escaping the solar system after its brief visit. In another scenario, Neptune's orbit might shift slightly, moving it either closer to the Sun or farther away. The exact outcome would depend on many factors: the mass of the rogue planet, its speed relative to the Sun, the angle of its approach, and the positions of the other giant planets at the time of the encounter. Fortunately, direct collisions between planets are extremely unlikely. Space is simply too vast, and planetary orbits occupy enormous volumes. But gravitational interactions do not require contact to reshape the architecture of a planetary system. Even distant encounters can leave lasting effects. As astronomers monitored Neptune's motion over the years, they would likely begin to see those effects unfold gradually. The planet's orbit might shift in ways that ripple outward to the Kuiper Belt, altering the paths of countless smaller bodies. Some of those objects might be nudged inward toward the Sun, eventually appearing as comets visible from Earth centuries later. Others might be pushed outward into the depths of interstellar space. In this way, Neptune would act as both a witness and a participant in the unfolding encounter between the solar system and the wandering planet. Its gravitational field would respond to the visitor, and in doing so it would help transmit the disturbance deeper into the solar system. Because once Neptune's orbit began changing, however slightly, those changes would not remain isolated. Every planet in the solar system is connected through gravity. A shift in Neptune's motion would subtly influence Uranus. Uranus would, in turn, pass along small disturbances to Saturn. Saturn's immense gravity would interact with Jupiter, and Jupiter, the most massive planet of all, exerts strong gravitational influence throughout the solar system. For billions of years, the planets of our solar system have followed paths that are remarkably stable. Each one travels along its own orbit around the Sun, shaped by gravity and refined over immense stretches of time. These paths are not perfectly circular, and they are not completely isolated from one another, but they remain predictable enough that astronomers can calculate their positions with extraordinary precision. In fact, planetary orbits are so well understood that scientists can project them thousands or even millions of years into the future using computer simulations. The solar system behaves like a vast mechanical system, where gravity acts as the invisible framework holding everything together. But this stability is not absolute. The solar system is better described as a delicate balance rather than a rigid structure. Every planet pulls on every other planet. Those gravitational interactions are normally small, yet they accumulate slowly over time. The architecture we see today is the result of billions of years of these interactions settling into relatively stable patterns. Introduce a new massive object into that system, however, and the balance begins to change. When the rogue planet first began influencing Neptune, the effects were subtle, almost whisper-like. Neptune's orbit shifted slightly, its path around the Sun adjusting in response to the new gravitational presence. As time passed and the wandering planet moved closer, those adjustments would grow more noticeable, not dramatic, but measurable. Neptune's orbit might become slightly more elongated, stretching a little farther from the Sun at one point and drawing slightly closer at another. The timing of its position in the sky would shift compared to long-established predictions. Astronomers studying the outer planets would recognize that the solar system was no longer behaving exactly as it had before. And because the planets interact gravitationally with one another, the disturbance would not remain confined to Neptune alone. Uranus, the next giant planet inward, would begin feeling the effects next. Uranus orbits the Sun at about 19 astronomical units, taking 84 Earth years to complete a single revolution. It is a massive world, 4 times the diameter of Earth, and surrounded by a system of rings and moons. Normally its orbit remains extremely stable, shaped primarily by the Sun's gravity and minor influences from Neptune and Saturn. But once Neptune's motion began shifting, Uranus would experience small gravitational nudges transmitted through the network of planetary interactions. These nudges might cause Uranus's orbit to adjust slightly. Perhaps its orbital speed would change by a tiny amount. Perhaps the orientation of its orbit would tilt by a fraction of a degree. These differences might sound insignificant, but in celestial mechanics, even very small variations can have meaningful consequences over long periods. Astronomers tracking Uranus would begin noticing that its predicted position differed slightly from observation. The discrepancy might be only a few kilometres at first, then perhaps tens or hundreds of kilometres as time passed. While that distance sounds large in everyday terms, it is extremely small compared to the billions of kilometres that define planetary orbits. Yet for scientists measuring planetary motion with incredible precision, such changes would be important clues. They would indicate that the gravitational influence of the rogue planet was spreading deeper into the solar system. Computer models would begin simulating not just the rogue planet's interaction with Neptune, but the cascading effects throughout the giant planet region. These models would reveal something fascinating about planetary systems. They behave less like a rigid clockwork and more like a complex dance. Each planet follows its own path, but every step is influenced by the others. When one dancer changes direction slightly, the rest of the choreography adjusts in response. In this sense, the solar system is a dynamic structure rather than a fixed one. It adapts, it evolves, and under the influence of a new gravitational participant, the dance begins to change. Saturn would eventually feel the disturbance as well. Saturn is a massive world, nearly 10 times the diameter of Earth, surrounded by its famous rings and dozens of moons. Its orbit lies about 9.5 astronomical units from the Sun, placing it well inside the region of the outer planets, but still far from the warmth of the inner solar system. Normally, Saturn's motion is influenced primarily by Jupiter, whose enormous mass dominates the planetary gravitational landscape. But if Uranus and Neptune began experiencing slight orbital shifts, those changes would propagate inward. Saturn's orbit might adjust in response. Again, the changes would be small. A tiny alteration in orbital speed, a slight modification to the timing of its position relative to Jupiter. Perhaps a subtle shift in the orientation of its orbit over long timescales. To astronomers studying planetary motion, these variations would confirm that the rogue planet's arrival was affecting the broader structure of the solar system. And still, life on Earth would continue normally. The sun would rise and set. The moon would move through its phases. Even the visible planets in the night sky would appear unchanged to the naked eye. The gravitational shifts unfolding across the solar system would operate on timescales far longer than a human lifetime. But within the calculations of scientists, the pattern would become increasingly clear. The solar system was adjusting to the presence of a new massive body. As these adjustments continued, attention would naturally turn to Jupiter. Jupiter is the largest planet in the solar system by a tremendous margin. Its mass is more than twice that of all the other planets combined. Because of this, Jupiter plays a critical role in maintaining the overall stability of planetary orbits. Its gravitational influence extends throughout the solar system. Asteroids in the main belt are shaped by Jupiter's gravity. Comets from distant regions are often redirected by its powerful pull. Even the orbits of other planets feel its influence. If disturbances from the rogue planet reach Jupiter through the chain of planetary interactions, the consequences could become far more significant. Jupiter acts as a kind of gravitational anchor for the solar system. Any change to its orbit, even a small one, could affect the overall dynamics of the planetary system. Fortunately, Jupiter's enormous mass also makes its orbit relatively resistant to disruption. A distant rogue planet would need to approach quite close to produce noticeable changes in Jupiter's motion. Still, astronomers would simulate every possibility. Some models might show that Jupiter's orbit remained almost entirely unaffected. Others might reveal slight shifts that propagate inward toward the inner planets over extremely long periods. At this stage, however, the rogue planet would still be far from Jupiter's region. Its most immediate influence would remain concentrated among the outer planets and the countless smaller objects scattered throughout the Kuiper Belt and beyond. Those smaller objects would respond dramatically compared to the giant planets. Many Kuiper Belt objects follow delicate orbital patterns maintained by resonances with Neptune. If Neptune's orbit changed even slightly, those resonances might shift or break. Some objects could be nudged into new paths. Others might be scattered outward or inward. Over centuries and millennia, the structure of the Kuiper Belt might slowly evolve in response to the rogue planet's passage. Comets that had remained dormant for billions of years could begin long journeys toward the Sun. New populations of icy bodies might be scattered into unfamiliar orbits. In this way, the outer solar system would become increasingly active as gravitational interactions unfolded. From Earth, astronomers might notice subtle increases in the number of long-period comets appearing in the sky. At first, such changes might seem coincidental, but over time, patterns would emerge linking those comets to disturbances in the distant frontier of the solar system. Meanwhile, the rogue planet itself would continue its inward journey. With each passing decade, its gravitational influence would grow stronger. The whispers felt by Neptune would become more pronounced. The adjustments to planetary orbits would become easier to detect, and the outer solar system would gradually transition from a stable, predictable environment into something slightly more dynamic, not chaotic, not catastrophic, but undeniably different from the calm gravitational arrangement that had existed for billions of years. At that point, astronomers would begin asking an even more interesting question. What would happen if the rogue planet moved close enough to interact directly with the giant planets themselves? For most of the solar system's long history, the outer planets have moved in an arrangement that appears calm and orderly. Jupiter, Saturn, Uranus, and Neptune circle the Sun along wide paths separated by vast distances. Their orbits rarely cross, and their motions follow predictable rhythms that astronomers have studied for centuries. Yet beneath that calm appearance lies something more complex. The outer solar system is not static. It is a gravitational ecosystem, a delicate network of massive worlds constantly influencing one another through invisible forces. Even though the giant planets are far apart, their gravity reaches across the emptiness between them. Jupiter tugs on Saturn. Saturn influences Uranus. Uranus and Neptune interact in smaller but still measurable ways. Over billions of years, these interactions have settled into patterns that are relatively stable, but the stability is not absolute. It depends on the current arrangement of masses and distances. Change one part of that system, and the entire balance begins to adjust. The arrival of a rogue planet would represent exactly that kind of change. By the time the wandering world moved into the region of the outer planets, its presence would already be well known to astronomers. Its trajectory would have been tracked for decades, perhaps even centuries, and computer models would have explored countless possible futures. Still, there would be uncertainty. Gravitational interactions between massive bodies are notoriously sensitive to small details. A difference of only a few thousand kilometers in the path of a passing planet could lead to noticeably different outcomes over long time scales. And so, as the rogue planet approached the giant planets, the solar system would enter a phase that scientists might describe as dynamically interesting. At first, Neptune would remain the primary participant in this interaction. Being the outermost major planet, it would likely be the first to encounter the wandering world at relatively close range. Imagine two massive planets passing one another across a distance of several million kilometers. That might sound enormous, but in astronomical terms it can count as a close encounter. During such a flyby, the gravity of each planet would tug strongly on the other. They would not collide. The vastness of space makes direct impacts between planets extraordinarily unlikely, but gravity alone is enough to exchange energy between the two bodies. In a gravitational encounter, one object can gain energy while the other loses it. This exchange changes the shapes and sizes of their orbits around the Sun. If the rogue planet approached Neptune in the right way, Neptune might lose a tiny amount of orbital energy, moving slightly closer to the Sun. At the same time, the rogue planet could gain energy, sending it onto a wider trajectory that carries it farther outward again. In another scenario, the opposite might occur. Neptune could gain energy and drift slightly outward, while the rogue planet becomes more tightly bound to the Sun's gravitational field. These changes would not happen instantly. The encounter would unfold over months or years as the two planets move through their respective orbits. their gravitational fields would interact continuously during that time, slowly adjusting their motions. Astronomers observing the event would analyse every detail. Precise measurements of Neptune's position would be compared with predictions from earlier models. Even tiny changes in its orbit would provide valuable clues about how the gravitational exchange was unfolding. Meanwhile, the rogue planet itself would continue moving deeper into the solar system. If its trajectory carried it past Neptune toward Uranus, the gravitational story would become even more complicated. Uranus occupies a region of space roughly 19 astronomical units from the Sun. It is a massive world, tilted dramatically on its side, with a system of rings and moons quietly accompanying it on its long journey around the Sun. Under normal conditions, Uranus and Neptune maintain a relatively stable gravitational relationship. But if a rogue planet disturbed Neptune's orbit even slightly, Uranus would eventually feel the effects. The disturbance might arrive in the form of subtle gravitational nudges passed along through the planetary network. Neptune shifts slightly. That shift influences Uranus. Uranus then interacts differently with Saturn and Jupiter. In this way, a change introduced in the outermost region of the solar system begins rippling inward through the entire planetary system. Should the rogue planet pass close enough to Uranus itself, another gravitational exchange could occur. Once again, the two planets might trade energy. Uranus could gain or lose a small amount of orbital speed. Its path around the Sun might stretch slightly into a more elliptical shape. The rogue planet's trajectory could change direction again, perhaps sending it on a path that takes it closer to Saturn. At this point, the outer solar system would resemble something like a slow-motion dance among enormous partners. Each world moves along its path, each gravitational encounter alters the rhythm. The changes are not chaotic in the everyday sense, but they are complex. Predicting the long-term outcome becomes increasingly difficult as more interactions occur. Astronomers would rely heavily on computer simulations to explore the possibilities. Modern simulations can model the gravitational interactions of many bodies at once, calculating their motions over thousands or even millions of years. Even so, tiny differences in starting conditions can lead to different long-term outcomes. Some simulations might show the rogue planet being flung back out of the solar system after its encounters with Neptune and Uranus. Others might show it settling temporarily into an elongated orbit around the Sun. Still others might reveal more dramatic rearrangements of the outer planet's orbits over long periods of time. One particularly important participant in this dance would eventually be Saturn. Saturn is not as massive as Jupiter, but it is still an enormous world with powerful gravitational influence. Its orbit lies about 9.5 astronomical units from the Sun, placing it well inside the region of Uranus and Neptune. If the rogue planet approached Saturn's orbit after interacting with the outer planets, the gravitational dynamics would become even more interesting. Saturn and Jupiter already share a delicate relationship. Their orbits are linked through gravitational resonances that help maintain long-term stability in the solar system. A new massive object moving through that region could temporarily disturb those resonances. Again, the likely effects would be small in the short term. Saturn might shift slightly inward or outward. Its orbital period might change by a fraction of a percent. But such changes could influence the motions of countless smaller objects in the asteroid belt and beyond. Meanwhile, the rogue planet's own future would become increasingly uncertain. Each gravitational encounter with a giant planet would alter its trajectory. In some cases, the rogue planet might receive a gravitational boost that accelerates it back toward the outer solar system. In others, it might lose energy and become more tightly bound to the Sun. One intriguing possibility is that the rogue planet could briefly become a temporary member of the solar system, following a long stretched orbit that carries it far beyond the known planets before returning again. Such an orbit might take tens of thousands of years to complete. Another possibility is that Jupiter itself would eventually play a decisive role. Jupiter's enormous mass gives it tremendous gravitational influence. If the rogue planet passed anywhere near Jupiter's orbit, the encounter could act like a powerful slingshot. The rogue planet might be flung outward at high speed, escaping the solar system entirely. Or, in a rarer case, Jupiter's gravity might capture the wandering world into a new orbit around the Sun. The exact outcome would depend on the geometry of the encounter, angles, speeds, distances, all the delicate details of celestial mechanics. Throughout this entire process, the outer solar system would be undergoing a subtle but fascinating transformation. The orbits of the giant planets might shift slightly. The Kuiper Belt could become more active as icy bodies are scattered into new trajectories. Long dormant comets might begin journeys toward the inner solar system, and through it all, the rogue planet would continue its slow passage among the giants. From Earth, these events would unfold gradually. Years would pass, decades would pass. Astronomers would study the encounter with growing excitement, recognizing that such an event offered a rare opportunity to observe planetary dynamics in action. Yet the most immediate consequences would remain far from the inner solar system, for now the giant planets would carry the burden of this gravitational dance. But as the rogue planet continued its journey, the disturbances created in the outer solar system would not remain confined there forever, because every change in the motions of the giant planets eventually influences the countless smaller bodies scattered throughout the solar system. Long before anyone on Earth would notice something unusual in the sky, the region between Mars and Jupiter would quietly begin to respond to changes unfolding far beyond it. This region, known as the asteroid belt, contains millions of rocky fragments left over from the early formation of the solar system. These objects range in size from tiny pebbles to dwarf planet-sized bodies hundreds of kilometers across. Most of them orbit the Sun in relatively stable paths, guided primarily by the Sun's gravity and influenced strongly by the enormous gravitational presence of Jupiter. Despite how crowded the asteroid belt may sound, the objects within it are actually separated by vast distances. Space between individual asteroids is usually millions of kilometers wide. If you were somehow drifting through the asteroid belt in a spacecraft, you would likely see nothing at all for long stretches of time. Still, these objects follow delicate orbital patterns that have remained stable for billions of years. The stability of the asteroid belt depends heavily on Jupiter. Jupiter's gravity acts almost like a sculptor, shaping the distribution of asteroids into specific regions. Some zones remain densely populated, while others are nearly empty. These gaps, known as Kirkwood gaps, appear where Jupiter's gravitational influence creates orbital resonances. In those regions, asteroids cannot maintain stable orbits because Jupiter repeatedly nudges them each time they complete certain fractions of an orbit, compared to Jupiter's own path around the Sun. Over time, those asteroids are pushed out of those unstable regions, leaving behind noticeable gaps. The structure of the asteroid belt, therefore, is not random. It is the product of an intricate gravitational balance that has existed for billions of years. But once the rogue planet entered the solar system and began disturbing the outer planets, that balance would begin to shift. The process would not happen suddenly. Instead, it would begin with small changes in the orbits of the giant planets themselves. Earlier, Neptune's orbit had been altered slightly by its encounter with the wandering world. That change slowly propagated inward through Uranus and Saturn. Even tiny shifts in those outer planetary orbits can eventually influence Jupiter. Because Jupiter is so massive, even a minute change in its motion can ripple across the asteroid belt. The gravitational relationship between Jupiter and the asteroids is extremely sensitive. Asteroids orbiting near resonant regions depend on precise timing in their paths around the Sun. If Jupiter's orbit changes slightly, even by a fraction of a percent, the locations of those resonances shift, and when resonances move, the asteroids trapped near them begin responding. Some asteroids might drift into newly unstable regions where Jupiter's gravity repeatedly tugs on them in the same orbital pattern. Each time the asteroid completes an orbit, Jupiter would pull on it again, gradually increasing the asteroid's orbital energy. The effect is slow but relentless. Over many years, the asteroid's path around the Sun would become more elongated. Eventually that asteroid might be pushed onto a trajectory that carries it far from the asteroid belt altogether. In some cases, such asteroids could be redirected toward the inner solar system. This process already happens occasionally even without a rogue planet. Jupiter's resonances occasionally push asteroids into new paths, sending them inward where they may cross the orbits of Mars, Earth, or Venus. These objects are known as near-Earth asteroids, and many of them originated in the asteroid belt before gravitational interactions altered their orbits. But if the rogue planet caused Jupiter's orbit to shift even slightly, the locations of many resonant zones would move. As a result, larger numbers of asteroids could begin drifting out of their stable positions. Over time, the asteroid belt might become more active. Clusters of asteroids could begin migrating into new orbits. Some might collide with one another as their paths intersect in new ways. These collisions would produce clouds of debris that slowly spread through space. Fragments from those collisions might themselves be nudged into unstable orbits by Jupiter's gravity. The result would be a gradual increase in the number of small rocky bodies moving toward the inner solar system. From Earth, astronomers might begin noticing a subtle rise in newly discovered asteroids with unusual orbits. Telescopes scanning the sky each night would detect more objects moving across the background stars. Most would remain harmless, their paths carrying them safely past the inner planets. But the increase itself would be noticeable. Scientists studying asteroid populations would analyze the data carefully. They might discover that many of the new objects originated from similar regions of the asteroid belt. Tracing their trajectories backward in time could reveal that their orbits had become unstable relatively recently. Eventually, researchers would connect this pattern with the earlier disturbances observed in the outer solar system. The gravitational ripple caused by the rogue planet had reached the asteroid belt. Of course, the asteroid belt itself contains some truly enormous objects. The largest is Ceres, a dwarf planet nearly 1,000 kilometers across. Several other bodies such as Vesta, Pallas and Hygeia also possess significant mass compared to typical asteroids. These larger objects have enough gravity to influence smaller asteroids around them. If the belt's overall structure began shifting, the interactions between these larger bodies and surrounding asteroids could create even more complex dynamics. Over long periods, the architecture of the asteroid belt might change. Regions once considered stable could become more active. Certain clusters of asteroids might disperse as gravitational influences shift their paths. Other regions might grow more crowded as objects migrate into them. Yet even during such changes, the asteroid belt would remain far from a chaotic swarm of rocks flying wildly through space. Orbital mechanics tend to smooth out extreme disturbances over time. Most asteroids would continue following predictable paths around the Sun. Still, the increased activity would be measurable. Astronomers would see more collisions, more debris clouds, more asteroids leaving the belt. Computer simulations would help scientists understand how the rogue planet's presence had indirectly triggered these changes. Researchers might even identify particular resonances that shifted due to Jupiter's slightly altered orbit. These discoveries would provide valuable insights into how planetary systems respond to external disturbances. Such insights would not only help explain events unfolding in our solar system, but also improve our understanding of planetary systems around other stars. After all, rogue planets may occasionally pass through other star systems as well. Observing how our own system responds would offer a rare opportunity to witness planetary dynamics on a grand scale. Meanwhile, the rogue planet itself would still be moving through the outer regions among the giant planets. Its trajectory would continue evolving as gravitational encounters subtly altered its path. Depending on those encounters, the wandering world might eventually move closer to the Sun or begin drifting outward again. Either outcome would influence how long its gravitational effects persisted within the solar system. If the rogue planet remained within the outer solar system for an extended period, the asteroid belt could experience decades or centuries of increased activity. The gradual scattering of asteroids would continue sending small rocky bodies toward the inner planets. Most would burn up harmlessly in planetary atmospheres. Others would remain as distant visitors passing safely by. But the pattern would remain unmistakable. The once stable asteroid belt would have awakened, and its activity would represent only one part of the larger story unfolding across the solar system. Out beyond the familiar planets, beyond the asteroid belt and the icy worlds of the Kuiper Belt, there exists a region so distant and sparse that it almost feels like the edge of the sun's influence. In this far-off territory, countless frozen bodies drift slowly through space, many of them unchanged since the earliest days of the solar system. These objects are comets. Unlike asteroids, which are primarily rocky, comets are made largely of ice mixed with dust and organic compounds. They are sometimes described as dirty snowballs, though many are far larger and more complex than that phrase suggests. Some comets measure only a few hundred meters across, while others span dozens of kilometers. Most of the time, these icy bodies remain extremely far from the Sun. The majority live in two distant reservoirs. The first is the Kuiper Belt, a flattened disk beyond Neptune where Pluto and many other icy dwarf planets reside. The second, far more distant region is the Oort cloud, a vast spherical halo that may stretch tens of thousands of astronomical units from the Sun in every direction. To understand just how distant that is, consider this comparison. Earth orbits the Sun at a distance of 1 astronomical unit, which is roughly 150 million kilometers. Neptune orbits at about 30 astronomical units. The Kuiper Belt begins around that distance and extends perhaps to 50 or 60 astronomical units, but the Oort cloud may begin thousands of astronomical units away and extend outward nearly a light year from the Sun. That distance represents the outer frontier of the Sun's gravitational influence. Objects in the Oort cloud orbit extremely slowly, sometimes taking millions of years to complete a single journey around the Sun. Their orbits are also fragile. Because the Sun's gravitational hold on them is weak, even small disturbances can alter their paths. Passing stars occasionally disturb this region. As stars drift through the Milky Way, some pass relatively near the solar system on cosmic timescales. When they do, their gravity can gently tug on objects in the Oort cloud. Sometimes those distant comets are nudged inward. They begin long journeys toward the Sun that can take tens of thousands of years to complete. Eventually, one of those travellers may appear in the inner solar system, glowing as sunlight warms its icy surface and releases gas and dust into a bright tail. Many of the spectacular comets visible from Earth originate this way. Now imagine a rogue planet drifting into the solar system from interstellar space. Such an object would represent a much stronger gravitational disturbance than a passing star. While stars usually pass several light years away, a rogue planet entering the outer solar system might travel directly through the region occupied by the Oort cloud. The effects of that passage could be significant. As the rogue planet moved through the outermost reaches of the Sun's domain, its gravity would begin pulling on nearby cometary bodies. Some comets would feel only a slight tug, their orbits shifting by small amounts. Others might experience stronger gravitational encounters. If a comet passed relatively close to the rogue planet, its orbit could change dramatically. Some comets might be pushed inward toward the Sun. Others might be flung outward entirely, escaping the solar system and becoming interstellar travellers themselves. Over time, these disturbances could send waves of comets toward the inner solar system, not all at once, not like a sudden storm. Instead, the process would unfold slowly over centuries or even millennia. A comet nudged inward from the distant Oort cloud might take tens of thousands of years before it finally reaches the inner solar system, where sunlight becomes strong enough to create the glowing tails we associate with comets. But if enough comets were disturbed by the rogue planet's passage, the rate at which new comets appeared could increase. Astronomers observing the night sky might notice that more long-period comets were arriving from distant regions of the solar system. Long-period comets are those with orbital periods longer than 200 years. Many of them have orbits lasting tens of thousands of years, meaning that once they pass through the inner solar system, they may not return for an extremely long time. These comets often approach from unpredictable directions because their orbits are shaped by disturbances in the distant Oort cloud. If a rogue planet stirred that region, astronomers might begin seeing patterns in the directions from which new comets arrived. Some might trace their paths back to the same region of space where the rogue planet had passed. Computer models would help researchers understand how the cometary reservoir had been disturbed. Simulations might reveal clusters of comets whose orbits had been altered during the rogue planet's journey through the outer solar system. For scientists studying the dynamics of comets, this would be an extraordinary opportunity. Normally, the Oort cloud is so distant that it cannot be observed directly. Its existence is inferred mainly from the behavior of long-period comets entering the inner solar system. But if a rogue planet perturbed that region, astronomers might be able to study how large-scale gravitational disturbances propagate through such a distant cloud of objects. Meanwhile, the comets themselves would begin long journeys toward the Sun. At first, they would remain invisible from Earth. Far from the Sun, comets are dark, frozen bodies reflecting very little light. But as they drifted inward over thousands of years, sunlight would gradually warm their surfaces. Ice would begin to sublimate, turning directly into gas. Jets of gas and dust would erupt from the comet's surface, forming a glowing atmosphere known as a coma. Solar radiation and the solar wind would then push some of that material away from the comet, creating the long luminous tails that stretch across the sky. Seen from Earth, such comets can be breathtaking. Throughout history, bright comets have captured the attention of observers around the world. Some have become famous visitors, appearing once in a lifetime before disappearing again into the depths of the solar system. If the rogue planet's passage stirred enough comets in the distant cloud, future generations might witness a gradual increase in such visitors. Over centuries, the number of newly arriving long-period comets could grow. Most would remain harmless, passing far from Earth before continuing their long orbits. But their presence would serve as a reminder that the outer solar system had been disturbed. Astronomers would carefully track each new comet. By calculating their orbits backward in time, they might identify clusters of comets originating from similar regions of the Oort cloud. Those patterns could reveal the path taken by the rogue planet as it moved through the outer solar system. Even long after the wandering world had passed, its gravitational influence could remain visible through the altered trajectories of these icy travellers. Yet the comets would not be the only objects affected. Many smaller icy bodies might also shift into new orbits within the Kuiper Belt and scattered disk regions. Some of those objects might eventually become new short-period comets, visiting the inner solar system more frequently. In this way, the rogue planet's arrival would leave a lasting imprint on the outer solar system, not through catastrophic collisions or immediate upheaval, but through subtle gravitational changes that slowly reshape the population of distant icy bodies. Over long time scales, those changes would ripple inward. The asteroid belt had already begun responding through shifting resonances. The outer planets had adjusted their orbits slightly, as gravitational forces redistributed energy among them. And now the distant cometary reservoirs were beginning to stir. From Earth, these changes would appear gradual and distant. Life on our planet would continue much as it always had. But in the quiet darkness beyond Neptune, the gravitational story of the solar system would continue unfolding. Because while comets were beginning their slow journeys toward the Sun, the rogue planet itself had not yet completed its passage among the giant planets. Its path through the solar system would still depend on the outcome of its encounters with the massive worlds already orbiting the Sun. At some point during this long encounter, something remarkable would begin happening in the skies above Earth. Until now, everything unfolding in the outer solar system had been known mainly through telescopes, calculations, and patient observation. Astronomers had watched the rogue planet approach for years or even decades, tracking its position against distant stars while computer models explored its future path. But eventually the wandering world would move close enough to the Sun that sunlight reflecting from its surface would become easier to detect. the object would grow brighter. Not suddenly, and not dramatically at first, but steadily. Large telescopes would begin resolving it more clearly. What had once been a faint moving point in digital images would slowly reveal a disk, small but unmistakably planetary in nature. At that stage, the rogue planet would still be extremely far from Earth. Even if it were as large as Neptune, its distance might still place it well beyond the orbit of the outer planets. To the naked eye, it would remain invisible, buried within the faint background of stars. But astronomers would know exactly where to look. Observatories around the world would begin pointing their instruments toward it regularly. Spectrographs would analyze the light reflecting from its atmosphere or surface. Infrared telescopes would measure its temperature. Space telescopes might capture detailed images revealing its color, cloud patterns, or even faint rings or moons. Scientists would be eager to learn everything possible about this unexpected visitor. Was it a gas giant like Neptune or Jupiter? A frozen world with thick clouds of methane? A rocky planet surrounded by a thin atmosphere? Each possibility would tell a different story about where the rogue planet might have formed. If the planet resembled Neptune, with a thick atmosphere of hydrogen, helium and methane, it likely formed far from its original star before being ejected from its birth system. If it appeared rocky and dense, perhaps similar in size to Earth or Mars, it might have originated closer to a star before gravitational chaos cast it out into interstellar space. Even subtle details in the planet's atmosphere could provide clues. Astronomers might detect traces of water vapor, methane, ammonia, or other gases. Those chemical fingerprints would help reconstruct the environment in which the planet formed long ago. In this way, the rogue planet would become more than just a passing curiosity. It would be a scientific treasure. Studying it would provide a rare opportunity to examine a world from another planetary system without leaving our own. Meanwhile, its brightness in the sky would continue increasing as it moved closer to the Sun. Eventually, the planet might grow bright enough to be seen through modest backyard telescopes. Amateur astronomers around the world would join the effort to observe it. Sky maps would circulate online showing where to find the object among familiar constellations. At first, it might appear as a faint star-like point slowly drifting across the sky over weeks and months. Unlike stars, which remain fixed relative to one another, planets move gradually against the stellar background as they orbit the Sun. This wandering motion is exactly how ancient astronomers first recognized the planets thousands of years ago. Now humanity would witness the arrival of a new wandering world. News of the discovery would spread quickly. Headlines might announce that a rogue planet from interstellar space was now visible through telescopes. Public interest would grow as people realized that a completely new planet had entered the solar system. Artists and scientists alike would speculate about what the world might look like up close. If the planet possessed a thick atmosphere, enormous storm systems might swirl across its surface. If it were an icy giant, vast clouds of methane could give it a deep blue or green colour similar to Neptune. Some models might even suggest the presence of moons orbiting the planet, small companions that had remained bound to it during its long journey through the galaxy. Those moons would be fascinating objects in their own right. For billions of years, they might have orbited their parent planet in complete darkness, warmed only by internal heat or faint starlight from distant suns. Now they would be illuminated by the sun for the first time since their exile began. The changing environment could produce surprising effects. Ices frozen for eons might begin sublimating. Thin atmospheres could form temporarily as sunlight warms the surface. These possibilities would excite scientists who study planetary atmospheres and icy worlds. Yet despite all the excitement, the rogue planet would still remain extremely distant from Earth. Even if it passed within the orbit of Neptune, the distance between our planet and the visitor would still be billions of kilometers. For most people, it would remain a faint object requiring telescopes to see clearly. But knowing that a new world had entered the solar system would carry a powerful psychological impact. humanity has always been fascinated by the discovery of new planets. When Uranus was discovered in 1781, it expanded the known boundaries of the solar system for the first time in recorded history. Neptune's discovery in 1846 confirmed that mathematics could predict unseen worlds. The detection of Pluto in 1930 revealed that icy bodies existed beyond the giant planets. Now, centuries later, a rogue planet arriving from interstellar space would represent an entirely new kind of discovery. It would not simply be another member of the solar system that had been hiding unseen. It would be an immigrant from another stellar neighborhood, a traveler that had wandered the galaxy before arriving here. Astronomers would track its motion with extreme care. The most important question would still remain: how close would it come? As observations accumulated, scientists would refine calculations of its orbit. They would determine whether the planet would pass through the outer solar system and depart again, or whether gravitational encounters with the giant planets might alter its trajectory in more dramatic ways. Each new observation would reduce the uncertainty. Slowly, a clearer picture would emerge. If the rogue planet's path carried it inward toward the region of the giant planets, the gravitational interactions already underway could intensify. Jupiter and Saturn, with their immense masses, could potentially alter the visitor's orbit significantly. Some simulations might show the planet being slingshot back toward interstellar space. Others might suggest that the Sun's gravity could capture it temporarily, placing it into a long, stretched orbit around the Sun. In that case, the rogue planet might remain part of the solar system for thousands or even millions of years before eventually escaping again. From Earth's perspective, such a captured world would slowly move across the sky over decades. Its brightness might vary as its distance from the Sun changed. Future generations could watch it approach and recede over centuries, but all of these possibilities would still depend on the precise path the rogue planet followed. At this stage, astronomers would continue refining their models. More observations, more simulations, more careful study of the gravitational dance unfolding among the giant planets. Yet while the scientific community focused on those calculations, people on Earth might simply look up at the sky and wonder. A new world had arrived. A planet that had spent billions of years drifting between the stars was now reflecting the light of our Sun. And though it remained distant and faint, its presence would remind humanity that the solar system is not completely isolated. The galaxy is full of wandering worlds. Sometimes one of them passes close enough to be seen. But while the rogue planet's appearance in our skies would capture the imagination of observers on Earth, scientists would still be watching something else even more carefully. They would be studying the effects that this visitor might have on the orbit of our own planet. Because although Earth lies far from the outer solar system, the gravitational influence of a large wandering planet could still travel inward through the network of planetary interactions. And that possibility would raise an important question. If a rogue planet entered the solar system and began interacting with the giant planets, could the chain of gravitational influences eventually reach all the way to Earth? And if it did, could our own planet's orbit around the Sun change in any meaningful way? The short answer is that it could, but the details matter enormously. Planetary orbits are shaped by gravity, and gravity is never truly isolated. Every planet pulls on every other planet. The Sun dominates the system, holding everything together, yet the smaller influences from neighbouring worlds still exist and accumulate over time. Even now, Earth's orbit is not perfectly fixed. Jupiter, with its enormous mass, slightly alters the shape of Earth's orbit as both planets move around the Sun. Saturn contributes small influences as well. These interactions cause slow variations in Earth's orbit that unfold over tens of thousands or hundreds of thousands of years. Scientists call these long-term changes Milankovitch cycles. They alter the tilt of Earth's axis, the shape of its orbit, and the orientation of that orbit relative to the Sun. These cycles are believed to play a role in the timing of ice ages by affecting how sunlight is distributed across the planet over very long periods. The important point is that Earth's orbit already shifts slightly, because of gravitational interactions with other planets, but those changes are small and gradual. Now imagine adding a rogue planet into the system. If the visitor remained in the distant outer regions and passed through without coming close to the giant planets, the effect on Earth would be essentially negligible. At such enormous distances, the Sun's gravity overwhelms everything else, and the influence of the rogue planet would fade quickly with distance. But if the wandering world interacted strongly with the giant planets, particularly Jupiter or Saturn, then the situation could become more interesting. Jupiter is the key player in this scenario. It contains more than twice the mass of all the other planets combined. Its gravitational influence extends throughout the solar system. When Jupiter's orbit changes even slightly, the effects ripple outward and inward through the entire planetary system. If a rogue planet were massive enough and passed close enough to Jupiter, the two worlds could exchange orbital energy during their encounter. Jupiter might shift slightly inward or outward in its orbit around the Sun. The change might be small in absolute terms, perhaps a fraction of 1% of its orbital distance. Yet even a small shift in Jupiter's orbit can alter the gravitational environment experienced by the inner planets. Computer simulations of planetary systems have shown that the arrangement of giant planets plays a major role in determining long-term orbital stability for smaller worlds. If Jupiter's orbit changed, the pattern of gravitational resonances within the solar system would change as well. These resonances act like subtle timing relationships between planetary orbits. When planets orbit the Sun in certain ratios relative to one another, their gravitational tugs occur at repeating intervals. Sometimes those interactions stabilize orbits. Other times they amplify small disturbances over long timescales. If the rogue planet's arrival altered Jupiter's orbit enough to shift those resonances, Earth's orbit might gradually adjust in response. This would not happen overnight. Orbital changes on planetary scales unfold over extremely long periods. Even significant gravitational disturbances can take thousands or millions of years to produce noticeable effects. Still, the possibility would be studied carefully. Astronomers would run detailed simulations modelling the future of the solar system under different scenarios. They would test how Earth's orbit responded if Jupiter moved slightly inward. They would explore what might happen if Saturn's orbit changed as well. They would calculate how the rogue planet's trajectory influenced the entire system. Most simulations would likely show reassuring results. The solar system is surprisingly resilient. Even when disturbed, the gravitational relationships among the planets tend to settle into new stable arrangements. Earth's orbit might become slightly more elliptical. Its distance from the Sun might change by a small amount. But the planet would almost certainly remain safely bound to the Sun. The dramatic idea of Earth being flung out of the solar system is extraordinarily unlikely, unless a planet the size of Jupiter passed extremely close to Earth itself. And such an encounter would be so improbable that astronomers consider it effectively impossible within the timescales of this scenario. Instead, any influence on Earth would likely appear as subtle orbital adjustments. For example, the shape of Earth's orbit might become slightly more elongated. Right now, Earth's orbit is nearly circular. The difference between its closest approach to the Sun and its farthest distance is relatively small. But gravitational interactions with other planets can increase or decrease that orbital eccentricity over time. If the rogue planet's arrival altered Jupiter's orbit, those long-term variations might shift. Earth's orbit might become a little more elliptical, or it might become even more circular than it already is. These differences could affect Earth's climate over geological timescales. When a planet's orbit becomes more elongated, the difference between its closest and farthest distances from the Sun grows larger. That can influence seasonal temperature patterns and long-term climate cycles. However, the magnitude of such changes would likely remain modest. Earth's climate has experienced many natural variations throughout its history, including ice ages and warm periods driven by orbital changes. The planet's atmosphere, oceans, and biosphere have adapted to those shifts many times before. In this scenario, any orbital adjustments would likely unfold slowly enough for Earth's climate system to respond gradually. Another possibility scientists would examine involves Earth's orbital tilt. The tilt of Earth's axis, currently about 23.5 degrees, is responsible for our seasons. That tilt is not perfectly fixed. It slowly oscillates between about 22 and 24.5 degrees over tens of thousands of years. Gravitational interactions with the Moon and other planets influence this cycle. If the giant planet's orbits changed, the timing and range of those oscillations might shift slightly. That could influence the intensity of seasonal differences over long timescales. Yet again, the changes would be gradual rather than sudden. From a human perspective, daily life would continue normally. The sun would still rise each morning. The moon would still orbit Earth. The familiar rhythm of seasons would continue, though perhaps evolving slowly across thousands of years. Astronomers studying the solar system would monitor these developments closely. Improved models of planetary motion would incorporate the rogue planet's influence. Observations of Earth's orbit would be compared with predictions to see how the system was responding. Over time, scientists would likely gain a deeper understanding of how planetary systems adapt to disturbances. Our solar system would become a natural laboratory for studying gravitational dynamics on a grand scale. Meanwhile, the rogue planet itself would continue its journey. Whether it eventually escaped the solar system or settled into a long-stretched orbit around the Sun, its passage would leave behind subtle changes in the architecture of the planetary system. Those changes might influence the motions of asteroids, comets, and planets for millions of years. If a rogue planet disturbed the solar system's gravitational balance, could Earth's climate itself begin to change as a result? Climate on Earth is shaped by an intricate balance of factors: sunlight reaching the planet's surface, the tilt of Earth's axis, the shape of its orbit around the Sun, the circulation of oceans and atmosphere, and even the distribution of continents all contribute to the conditions we experience at the surface. None of these factors remain perfectly constant forever. Over geological timescales, Earth's climate has shifted many times. Ice sheets have advanced and retreated across continents. Tropical regions have expanded and contracted. Forests have replaced deserts, and deserts have replaced forests. These changes did not happen randomly. They were driven by a combination of internal processes within Earth's climate system and external influences related to the planet's orbit. One of the most important of those external influences involves the slow variations in Earth's orbit and rotation known as Milankovitch cycles. These cycles operate over tens of thousands to hundreds of thousands of years. They include three main components: the shape of Earth's orbit, the tilt of Earth's axis, and the slow wobble of that axis as the planet spins. Even small changes in these parameters can alter how sunlight is distributed across Earth's surface. When the orbit becomes slightly more elliptical, the difference between Earth's closest approach to the Sun and its farthest distance becomes larger. When the tilt of Earth's axis changes, the intensity of seasons shifts, and when the orientation of the orbit slowly rotates, the timing of seasons relative to Earth's position in its orbit changes as well. These orbital variations have been linked to the timing of ice ages throughout the past few million years. Now imagine that the arrival of a rogue planet had altered the gravitational balance among the giant planets, which in turn caused small changes in Earth's orbit. The first thing scientists would examine would be the magnitude of those changes. If Earth's orbital distance from the Sun shifted slightly, the amount of solar energy reaching the planet could change by a small amount. Even a few % difference in solar energy can influence long-term climate patterns, but most likely the changes would be more subtle than that. More realistic scenarios suggest that Earth's orbit might become slightly more elliptical, or that the timing of Milankovitch cycles might shift. In that case, the overall amount of sunlight reaching Earth would remain similar, but its seasonal distribution could evolve gradually. For example, if Earth's orbit became a bit more elongated, winters in one hemisphere might occur when the planet is slightly farther from the Sun, making them colder on average. Summers in that same hemisphere might become somewhat warmer if they occurred when Earth was closer to the Sun, these differences would not transform the planet overnight. Climate systems respond slowly to changes in solar energy. Oceans store enormous amounts of heat and release it gradually over time. Ice sheets grow and melt across thousands of years rather than decades. But over long periods, the cumulative effects could become noticeable. Regions that currently experience moderate seasonal differences might develop more pronounced winters and summers. Polar ice sheets could expand if cooler conditions persisted long enough. Alternatively, warmer summers might accelerate melting in some regions, shifting the balance in the opposite direction. Earth's atmosphere would play a critical role in moderating these changes. The atmosphere acts as a complex regulator, distributing heat through winds, clouds, and precipitation patterns. Ocean currents perform a similar function by moving warm and cold water around the planet. If orbital changes altered the distribution of sunlight slightly, these systems would respond by redistributing energy across the globe. The result would likely be gradual shifts in climate zones. Deserts might expand or contract depending on how atmospheric circulation changed. Rainfall patterns could shift, influencing ecosystems and agricultural regions. Some areas might experience longer growing seasons, while others might face colder winters. Yet it is important to remember that Earth's climate has always been dynamic. During the last ice age, massive glaciers covered much of North America and Northern Europe. Sea levels were lower, and ecosystems looked very different from those of today. Despite those dramatic differences, life on Earth persisted and adapted. In the scenario involving a rogue planet, the changes affecting Earth's orbit would probably be much smaller than those that occurred during major geological events in the planet's past. Another factor to consider would be the timescale over which these changes occurred. Planetary orbital adjustments unfold extremely slowly. Even if the rogue planet altered the orbits of Jupiter or Saturn, the resulting effects on Earth's orbit might take tens of thousands or hundreds of thousands of years to become fully apparent. Human civilization, which has existed for only a few thousand years in its current form, would experience only a small portion of that gradual transformation. Future generations of scientists might track these orbital changes through precise measurements of Earth's motion around the Sun. Spacecraft and observatories already measure planetary positions with astonishing accuracy. Even tiny variations in Earth's orbit can be detected through careful analysis of spacecraft telemetry and astronomical observations. If orbital changes were occurring, scientists would likely understand them long before they produce noticeable effects on climate. This knowledge would allow humanity to anticipate long-term environmental trends. Understanding how Earth's orbit evolves could help researchers predict future climate shifts and prepare for gradual changes in ecosystems, sea levels, and weather patterns. Eventually, after years of careful observation and calculation, astronomers would know when the rogue planet would come closest to the Sun. This moment would not arrive suddenly or dramatically. Instead, it would be the natural midpoint of a long gravitational journey that had already been unfolding for decades. By that time, the wandering world would no longer be a faint mystery in telescope images. Scientists would have measured its orbit with remarkable precision. Its size, mass, and composition would likely be well understood. Researchers would know whether it resembled a gas giant like Neptune, an icy planet wrapped in frozen clouds, or a dense rocky world that once orbited another star. Still, the moment when the rogue planet reached the nearest point in its path around the Sun would remain important. In astronomy, that closest point is known as perihelion. Every object that orbits the Sun follows an elliptical path, and along that path there is always a position where the object is closest to the Sun, and another where it is farthest away. For the rogue planet, perihelion would represent the point at which its gravitational influence within the solar system reached its greatest strength. Even then, however, the event would likely be far less dramatic than popular imagination might suggest. The solar system is vast. The distances between planets are enormous. Even if the rogue planet passed within the region occupied by the giant planets, it might still remain billions of kilometers from Earth. For observers on our planet, the sky would appear almost unchanged. The sun would still dominate the daytime sky. The familiar planets would still move along their predictable paths. Only those who knew where to look through telescopes would be able to follow the slow movement of the visiting world. Yet scientifically, this moment would be extraordinary. Astronomers would watch closely as the rogue planet moved through the inner edge of the giant planet region. Its path might carry it somewhere between the orbits of Neptune and Saturn, or perhaps even closer depending on the outcome of earlier gravitational interactions. Wherever its path lay, the planet's motion would reveal much about the forces shaping the solar system. As the rogue planet approached perihelion, its speed would increase. This happens because objects orbiting the Sun move faster when they are closer to it. The Sun's gravity pulls them inward, converting gravitational energy into motion. Once the object passes its closest point and begins moving away again, its speed gradually decreases. For the rogue planet, this increase in speed could be significant. If it had entered the solar system travelling through interstellar space, it might have approached the Sun on a long stretch trajectory. As it fell deeper into the Sun's gravitational well, its velocity would increase. At perihelion, it would be moving faster than at any other point in its journey through the solar system. Astronomers would monitor this motion carefully. Every slight change in the planet's trajectory could reveal new details about how gravity from the Sun and the giant planets was influencing it. Meanwhile, the giant planets themselves would still be responding to the visitor. Neptune and Uranus, having already experienced the strongest early interactions, might now be slowly settling into slightly adjusted orbits. Saturn and Jupiter would continue exerting their enormous gravitational influence, subtly shaping the rogue planet's path as it moved through their region. Computer simulations would be running continuously at research centres around the world. Scientists would compare real observations of the planet's motion with predicted models, refining their understanding of the encounter in real time. Some simulations might show the rogue planet continuing on a trajectory that eventually carries it back out of the solar system. Others might indicate that the Sun's gravity has captured it into a long, elongated orbit. That possibility would be particularly fascinating. If the rogue planet lost enough energy during its passage among the giant planets, it might become gravitationally bound to the Sun. In that case, the moment of perihelion would mark the turning point in its story. Instead of continuing outward into interstellar space, the wandering world would begin climbing slowly away from the Sun along a new orbital path. This orbit might extend far beyond the known planets, perhaps thousands of astronomical units, into the distant reaches of the solar system. But eventually, after thousands or tens of thousands of years, the planet would return again. From the perspective of Earth's sky, such a captured world would behave like a very distant, slow-moving planet. For many years after perihelion, it would gradually drift farther from the Sun, becoming dimmer and harder to observe. Generations of astronomers might continue tracking it as it slowly retreated into the outer darkness. If the rogue planet were not captured, however, the moment of closest passage would mark the beginning of its departure. Once it moved beyond perihelion, the Sun's gravity would begin slowing it down as it climbed away from the inner solar system. The giant planets might still influence its path slightly, but the general direction of travel would carry it outward. Over the course of years, then decades, the planet would drift farther from the Sun. Its brightness would fade. Telescopes that once tracked it easily would require longer exposures to detect it. Eventually, the visitor might return to the region beyond Neptune, then beyond the Kuiper Belt. From there, it would continue into the distant Oort cloud, and beyond that, once again into interstellar space. Yet even as it departed, the rogue planet would leave behind subtle changes in the solar system. The orbits of the outer planets might remain slightly adjusted. The asteroid belt might continue sending small numbers of disturbed objects inward. The distant comet reservoirs might still produce visitors whose journeys began during the rogue planet's passage. These effects could persist for millions of years. Meanwhile, the knowledge gained during this encounter would reshape how scientists understand planetary systems. For the first time in human history, astronomers would have observed a full planetary flyby from another star system. They would have watched how a rogue planet interacts with an established system of planets. They would have measured the resulting gravitational changes with unprecedented precision. The data collected during this period would help scientists understand how planetary systems evolve, how planets are ejected into interstellar space, and how wandering worlds might occasionally interact with other stars. From a broader perspective, the encounter would also offer a reminder of something profound. The solar system is not an isolated island. It exists within a galaxy filled with stars, planets, and drifting worlds that occasionally pass near one another over cosmic timescales. Most of the time, those encounters occur at distances too large to produce noticeable effects. But sometimes, a wandering planet crosses paths with a star system like ours, and when that happens, the quiet gravitational balance of the system shifts, even if only slightly. For the rogue planet itself, the moment of closest passage would represent just another turning point in a journey that may have lasted billions of years. Long before arriving here, it might have formed around a distant star, only to be thrown into the darkness between stars by gravitational chaos. For eons it might have drifted through the cold emptiness of interstellar space. Then, for a brief chapter in its long existence, it would have passed near the Sun. And after that brief visit, the wandering world would continue on its path through the galaxy. But its departure would not necessarily mean the end of the story. Not every encounter between a star system and a wandering planet has to end with the visitor leaving again. Under the right conditions, gravity can transform a passing traveller into a long-term resident. This possibility would depend on a delicate exchange of energy during the rogue planet's journey through the solar system. When an object approaches the Sun from interstellar space, it normally arrives with enough speed to escape again after passing through the system. The Sun's gravity accelerates it as it falls inward, but unless something removes part of that energy, the object will simply slow down again as it climbs back out and eventually return to interstellar space. That is the usual outcome for interstellar visitors. The objects Oumuamua and 2I/Borisov, for example, both followed paths that allowed them to pass through the solar system once before continuing on their way through the galaxy. But planets are far more massive than those small bodies, and massive planets interact strongly with other planets through gravity. During a close encounter between two large worlds, orbital energy can be exchanged. One planet may gain energy while the other loses it. This exchange can change the shape and size of their orbits around the Sun. If the rogue planet lost enough orbital energy during an interaction with one of the giant planets, most likely Jupiter or Saturn, its trajectory could change in an important way. Instead of following an open path that carries it back into interstellar space, it might become gravitationally bound to the Sun. In other words, the Sun could capture the wandering planet. Such a capture would not necessarily place the new world into a neat circular orbit like those of the familiar planets. Instead, the orbit would probably be extremely elongated. At one end of the orbit, the rogue planet might come relatively close to the giant planets. At the other end, it could travel thousands of astronomical units away into the distant outer reaches of the solar system. Completing a single orbit might take tens of thousands of years. From Earth, the captured world would appear only occasionally, growing brighter as it approached the inner part of its orbit before slowly fading again as it moved outward. For most of its time, it would remain far beyond the reach of even powerful telescopes. Yet its presence would still influence the solar system. A massive planet travelling along such a long orbit would periodically pass through the region of the outer planets. Each passage could produce small gravitational interactions with Neptune, Uranus, or Saturn. Over millions of years, these repeated encounters might gradually reshape parts of the outer solar system. For example, the rogue planet could scatter objects in the Kuiper Belt into new orbits. Some icy bodies might be pushed inward, becoming comets that eventually visit the inner solar system. Others might be flung outward into interstellar space. The scattered disk, a region of icy objects with highly elongated orbits, might become even more populated as gravitational interactions continue over long timescales. In this way, the captured planet would act as a distant gravitational sculptor, slowly rearranging the distribution of small bodies at the edge of the solar system. Astronomers would study these effects carefully. By analysing the motions of distant objects, they could learn how the rogue planet's gravity was shaping the outer solar system. In fact, some scientists already suspect that unknown massive bodies may exist far beyond Neptune, because certain groups of distant objects show unusual orbital alignments. If a captured rogue planet existed, it could help explain patterns like these. Another fascinating possibility would involve the rogue planet's own system of moons. Many planets form with natural satellites, and it is entirely possible that the wandering world would have brought some of its moons with it during its journey through interstellar space. Those moons might have spent billions of years orbiting their parent planet in darkness. Once captured by the Sun, however, their environment would change. Each time the rogue planet moved closer to the Sun, sunlight would reach its moons more strongly. Surface ice might sublimate into thin atmospheres. Seasonal cycles could appear for the first time in the history of those distant worlds. Some moons might even possess subsurface oceans warmed by tidal interactions with their planet. If so, they could represent intriguing targets for future exploration. Imagine a moon that formed around a planet in another star system and later arrived within our own. Studying such a world could provide direct insight into planetary environments beyond the Sun. Over the centuries following the capture, astronomers would continue refining the rogue planet's orbit. Space telescopes and deep space probes might be designed specifically to study it. Because the planet's orbit would be so long, missions might take decades to intercept it at the right moment. Yet the scientific reward could be extraordinary. Instead of travelling to another star system to study an alien planet, humanity would have one visiting its own. Of course, the presence of a new planet in the solar system would also raise questions about long-term stability. Would the new orbit remain stable over billions of years, or might the rogue planet eventually escape again after additional gravitational interactions? Computer simulations would help scientists explore these possibilities. Many outcomes are possible in gravitational systems involving multiple massive bodies. In some scenarios, the rogue planet might remain in a distant orbit around the Sun for the remainder of the solar system's lifetime. In others, a future encounter with Jupiter or Saturn could send it back into interstellar space after millions of years. Either way, its capture would represent a rare event in the history of the solar system. Most planets remain permanently bound to the stars around which they formed. Rogue planets, on the other hand, are usually permanent wanderers. For one of those wandering worlds to be captured by another star is uncommon. Yet the galaxy is vast, and over billions of years even rare events can occur. If such a capture happened here, the solar system would gain a new member unlike any other. A planet that formed elsewhere. A world that drifted through the darkness between stars before finding a temporary home around the Sun. For astronomers, this would offer a remarkable opportunity. Studying that planet could reveal clues about planetary formation in other star systems, the processes that eject planets into interstellar space, and the ways star systems interact with wandering worlds. But whether the rogue planet ultimately stayed or departed, its passage through the solar system would already have answered an important question. We would know, with direct evidence, that the boundaries between planetary systems are not completely closed. The galaxy is full of wandering worlds. Sometimes they pass nearby, and occasionally one of them may even become part of a new planetary family. Yet even if such a planet remained in the solar system, its story would not end there, because every planet carries a history within it, a record of where it formed, how it evolved, and what environments it experienced during its long journey through space, an understanding that history would reveal something even more fascinating about the universe itself. A different outcome remains entirely possible. Instead of becoming a long-term resident of the solar system, the rogue planet might simply continue the journey it began billions of years earlier. After passing through the region of the giant planets and reaching the closest point in its path around the Sun, gravity could send it back outward again, returning it to the deep darkness between the stars. In many ways, this is the most likely result. Objects arriving from interstellar space typically carry tremendous momentum. Even though the Sun's gravity pulls them inward and accelerates them during their approach, they usually retain enough energy to escape once they begin moving away again. Unless a very specific gravitational interaction removes some of that energy, the visitor continues travelling through the galaxy just as it did before. If the rogue planet avoided a strong encounter with Jupiter or Saturn, its trajectory might remain largely unchanged. During its inward passage, it would have disturbed the outer solar system in subtle ways. Neptune's orbit may have shifted slightly. The Kuiper Belt might have scattered new objects into elongated paths. The distant comet reservoirs could have been stirred into sending fresh visitors toward the inner planets. But once the planet began moving away from the Sun again, its influence would gradually fade. The moment when it passed the region of closest approach would mark the turning point. From that point forward, the Sun's gravity would act like a gentle brake. As the rogue planet climbed away from the inner solar system, its speed would slowly decrease. Even though it would still be moving fast enough to escape, the gradual slowing would make its outward journey appear slower and quieter than its arrival. Astronomers would continue observing it carefully during this stage. The planet's motion across the sky would become slower each year as its distance increased. At first, it might still be visible through moderate telescopes, appearing as a faint disk drifting among background stars. But eventually, as the planet moved farther from the Sun, its brightness would diminish. Sunlight reflected from its atmosphere or surface would grow weaker with distance. A planet twice as far from the Sun receives only 1/4 as much sunlight. At 10 times the distance, the available sunlight becomes extremely faint. As a result, the rogue planet would gradually fade from view. Large research telescopes would track it for many years, refining measurements of its orbit and studying its physical characteristics while it remained observable. Spectroscopy would reveal details about its atmosphere. Infrared observations might detect heat escaping from its interior. If the planet possessed moons, astronomers might even detect subtle motions indicating the presence of those companions. But eventually the visitor would move beyond the range where detailed study was possible. After a few decades, only the largest telescopes might still detect it as a faint point. Then, over time, it would become too dim even for those instruments. Yet the story would not end there. Astronomers would continue predicting its future path using the data collected during its passage. Computer models would trace the planet's orbit outward through the solar system and beyond. These calculations would show how the Sun's gravity slowly loses its hold as distance increases. Somewhere far beyond the Kuiper Belt lies the region where the Sun's gravitational influence begins blending with that of the rest of the galaxy. At those enormous distances, tens of thousands of astronomical units, the pull of nearby stars and the gravitational field of the Milky Way itself become significant. If the rogue planet's orbit carried it that far, it would eventually escape the Sun's influence completely. At that moment, it would become once again what it had been before its arrival. A wandering planet drifting through interstellar space. The journey outward would take many thousands of years. Even travelling at high speed, crossing the vast outer reaches of the solar system requires immense time. The rogue planet might spend centuries moving through the distant Oort cloud region, passing among countless icy bodies that orbit the Sun at extraordinary distances. During that time, its gravity might continue nudging some of those distant objects into new paths. Some comets might be flung outward into interstellar space. Others might be sent inward toward the Sun on long, slow journeys that would not reach the inner solar system for tens of thousands of years. In this way, the rogue planet's passage could leave a lingering imprint on the solar system long after it had disappeared from telescopes. Future astronomers might notice clusters of long-period comets arriving from particular regions of space. Tracing their paths backward, they might eventually discover that those comets began their journeys during the era when the rogue planet passed through the outer solar system. Even after the visitor was gone, its gravitational fingerprints would remain visible. Meanwhile, the solar system itself would gradually settle into a new balance. Neptune, Uranus, and the other giant planets might retain slightly altered orbits. The asteroid belt could remain somewhat more active for a time as resonances shifted during the encounter. But over millions of years, gravitational interactions among the planets would slowly smooth out many of these disturbances. Planetary systems are remarkably good at finding new stable configurations after disturbances. The same process occurred billions of years ago during the early history of the solar system. Back then, the giant planets likely migrated through the outer regions, scattering debris and reshaping the architecture of the planetary system. Yet eventually, the system stabilized into the arrangement we see today. If a rogue planet passed through and departed again, the solar system would undergo a similar adjustment. The encounter would represent only a brief moment in the vast timeline of planetary evolution. For humanity, however, that moment would be unforgettable. Generations of astronomers would have spent years studying the visitor as it approached, passed near the Sun, and began its departure. Scientists would have gathered an unprecedented amount of data about a planet that formed in another star system. They would know its size, mass, atmosphere, and perhaps even details about its internal structure. If the planet possessed moons, their properties would have been studied as well. This information would provide valuable insight into how planetary systems form around other stars. Until now, most exoplanets discovered around distant stars have been detected indirectly. Astronomers observe subtle changes in starlight or gravitational effects to infer the presence of planets. Directly studying the surface or atmosphere of those distant worlds remains extremely challenging. But a rogue planet passing through the solar system would offer something very different. It would bring an alien world within reach of our telescopes. Instead of observing faint signals across light years of space, scientists would study a planet located within our own celestial neighbourhood. Even after the planet departed, the knowledge gained during its visit would continue shaping planetary science. Researchers would compare its composition with that of planets in the solar system. They might discover similarities suggesting that planet formation follows universal patterns across the galaxy. Or they might find surprising differences revealing new possibilities for how planets evolve. Either outcome would deepen humanity's understanding of the universe. The departing planet itself would continue travelling through the galaxy. For billions of years it might wander between stars, occasionally passing through other planetary systems just as it once passed through ours. Most of those encounters would occur at enormous distances. Rarely would the planet approach another star closely enough to interact strongly with its planets. But over cosmic timescales, such events become possible. Perhaps millions of years in the future, the rogue planet might pass near another star system. If that system contained planets of its own, similar gravitational interactions could occur again. Or perhaps the planet would remain alone, drifting through the dark spaces between stars indefinitely. The galaxy is vast, and the distances between stars are enormous. A wandering world might travel for billions of years without ever encountering another planetary system closely. From a cosmic perspective, the solar system would have been just one brief stop along that endless journey, yet for observers on Earth, the event would have been extraordinary. A world from another star would have passed through our celestial neighbourhood. Astronomers would have watched it arrive, measured its influence on the solar system, and followed its departure back into the darkness. The encounter would serve as a reminder that the boundaries between star systems are not rigid barriers. They are simply regions of space separated by enormous distances. Occasionally objects cross those distances. Comets drift from one system to another. Asteroids wander through interstellar space. And sometimes, entire planets travel the galaxy as lonely wanderers. If such a planet passed through the solar system and continued its journey outward again, it would leave behind more than scientific data. It would leave behind a powerful realization. Our solar system is not isolated. It is part of a much larger galactic environment where stars, planets, and wandering worlds move slowly through space over billions of years. And every so often those journeys intersect. When they do, even briefly, the quiet balance of a planetary system can shift just enough to reveal how connected the universe truly is. Yet after the rogue planet finally disappeared into interstellar space once again, one final question might linger in the minds of astronomers and observers alike, not about the planet that left, but about how often such encounters might happen across the vast history of the galaxy. Once the rogue planet had disappeared back into the darkness between stars, the solar system would slowly return to its familiar rhythm. The giant planets would continue tracing their enormous paths around the Sun. Asteroids would circle quietly between Mars and Jupiter. Distant comets would remain frozen in the far reaches of the Oort cloud. From the perspective of everyday life on Earth, the encounter would eventually become a historical event. Astronomers would still reference it in scientific papers. Students would learn about it in textbooks. Simulations would continue exploring the gravitational details of what happened during those years when the wandering world passed through our planetary neighbourhood. But the sky itself would look normal again. Yet the event would leave behind something far more important than a brief disturbance in orbital mechanics. It would change how humanity thinks about planets. For most of human history, planets were believed to exist only around stars. The ancient observers who first tracked the wandering lights in the sky, the 5 visible planets known in antiquity, assumed they were special objects moving through the heavens under the influence of divine order. Later, once the heliocentric model revealed that those planets were worlds orbiting the Sun, the concept expanded. Astronomers eventually realized that other stars likely had planets of their own. In the last few decades, that idea has been confirmed. Thousands of planets have been discovered around distant stars. These exoplanets come in astonishing varieties. Hot giants orbiting close to their stars, rocky worlds slightly larger than Earth, icy planets in distant orbits, and systems containing multiple planets, arranged in ways very different from our own solar system. But one discovery surprised scientists even more than the sheer number of planets. The galaxy appears to be full of rogue planets. These are worlds that do not orbit any star. Instead, they drift freely through interstellar space, travelling through the vast regions between stellar systems. Astronomers first suspected the existence of such planets when studying young star clusters. In those crowded environments, newly formed planetary systems can interact gravitationally with neighbouring stars. These interactions sometimes destabilise planetary orbits. A close encounter between 2 stars can tug strongly on the outer planets of a system. If the timing is right, one or more planets can be thrown completely out of their original systems. The process is known as planetary ejection. It happens more often than one might expect. Computer simulations of planetary system formation suggest that many systems experience periods of instability while their planets are settling into long-term orbits. During these chaotic early phases, some planets collide with each other, some fall into their stars and others are flung outward into interstellar space. Over billions of years, the Milky Way may have accumulated enormous numbers of such wandering worlds. In fact, some studies suggest that rogue planets could be nearly as common as stars themselves. Considering that the Milky Way contains hundreds of billions of stars, that possibility implies an astonishing number of lonely planets drifting through the galaxy. Detecting these objects is extremely challenging. Without a nearby star illuminating them, rogue planets are very faint. Most emit only a small amount of heat left over from their formation, which slowly fades as they cool over time. Astronomers occasionally detect them using a method called gravitational microlensing. When a rogue planet passes in front of a distant star from our perspective, its gravity briefly bends and magnifies the starlight. This effect can create a temporary brightening that reveals the presence of the otherwise invisible planet. Through such observations, scientists have begun confirming that rogue planets do exist. Some appear to be similar in mass to Jupiter, others may be closer in size to Earth. The galaxy, it seems, contains countless worlds that travel alone. Most of them likely wander through space for billions of years without encountering another planetary system. The distances between stars are simply too large for frequent interactions. Yet over cosmic timescales, rare encounters do happen. Stars orbit the centre of the Milky Way, moving through the galaxy like slow-moving ships across an ocean of space. As they travel, they occasionally pass relatively close to one another. When this happens, their gravitational fields can interact. Usually the effect is minor, but sometimes those encounters can perturb distant comets, or even capture or eject planets. Our own Sun has probably experienced many such distant encounters during its lifetime. Over billions of years, nearby stars may have passed within a few light years of the solar system. These events might have stirred the Oort cloud, sending occasional waves of comets inward, and it is entirely possible that rogue planets have passed near the solar system before. Most of those encounters would have happened far beyond the outer planets, leaving only subtle traces in the distant comet reservoirs. But the possibility that a wandering world might someday pass closer reminds us that the solar system exists within a dynamic galactic environment. It is not isolated. It moves through the Milky Way, along with billions of other stars and their planetary systems. During its orbit around the galaxy, which takes roughly 230 million years to complete, the Sun passes through different regions of space. Some of those regions may contain dense star clusters or clouds of gas and dust. Others are quieter regions where stars are more widely spaced. Over such long time scales, the solar system's surroundings change dramatically, and during those journeys, encounters with wandering worlds become possible. For astronomers, studying rogue planets offers a fascinating opportunity to understand planetary formation in new ways. A planet drifting alone through space still carries the chemical fingerprints of the environment in which it formed. By studying its atmosphere, composition, and internal heat, scientists can learn about the star system it once belonged to. If a rogue planet passed through the solar system and was observed closely, it could reveal details about distant planetary systems without requiring us to travel to them. In that sense, a wandering planet could act almost like a messenger from another star. Its chemistry could tell us about the materials present in its original system. Its mass and structure might reveal clues about how planets formed there. Even its moons, if it had any, could carry geological histories shaped by environments far beyond our Sun. The scientific value of such an encounter would be enormous, but beyond the scientific implications, there is also something deeply humbling about the idea of rogue planets. For billions of years, these worlds travel alone through the darkness. They do not orbit a sun. They receive almost no warmth or light. Yet they continue drifting through the galaxy, silent travellers moving along paths shaped only by gravity. Some may carry thick atmospheres trapping heat from their interiors. Others may host subsurface oceans hidden beneath layers of ice. It's even possible that life could exist in such environments, sustained not by sunlight but by chemical energy and geothermal heat. These possibilities remain speculative, but they remind us that the universe may contain far more diverse environments than we once imagined. The encounter with a rogue planet passing through the solar system would offer a brief glimpse into that broader cosmic story. For a few decades or centuries, humanity would observe a world that formed elsewhere. We would watch its gravitational influence ripple through our planetary system, and then, eventually, we would watch it depart again. The visitor would continue its long journey through the galaxy. Meanwhile, the solar system would return to its quiet stability. but the knowledge gained during that encounter would remain. We would know that planets are not confined to their birthplaces. They can wander, they can cross the immense distances between stars, and occasionally one of them may pass close enough for us to see. As the Sun continues its slow orbit around the Milky Way, it will pass through many different regions of the galaxy over the next billions of years. Some of those regions may contain more wandering planets than others. Perhaps another rogue world will pass near the solar system someday. Perhaps not. Either way, the universe is far larger and more dynamic than it once appeared. Stars form, planets are born, systems evolve, and sometimes worlds are cast out into the vast darkness between stars. Those wandering planets continue their silent journeys across the galaxy. And every so often, one of them briefly visits a new sun,